regions of 0. B to C, right here, goes something like this. That's 1 over r squared. And then it goes straight back to 0. All right, now let's look at where these charges might be located. So what is the charge on the inner surface of our smaller sphere, of our smaller shell? So if we are looking at this region right here, well, I know that the electric field must equal 0 here. There's no charge on the inside. There's nothing induced. It must equal 0. 0. What about the outer? Go right here. Well, what is our charge enclosed here? Plus 2q. It's everything. Everything is in there. We have an electric field due to a plus 2q charge. There it is. Plus 2q. What about our large shell? We go right on this inner diameter right here. Okay, we know that the electric field must equal 0 here. That means it needs to cancel with this plus 2q that's happening right here. That means all of the minus 2q is going to land at this surface. That's minus 2q. Then what about this outer surface? We have a net charge of 0 here. So outer must equal 0.
Welcome to EDU World Space.
Okay, so for this problem, we have an inner shell and an outer shell. And the inner shell has a charge of
Welcome
plus
to
2q.
EDU
The
World
outer shell
Space.
has a charge of plus 4q. The inner shell is bound by the inner shell, and an outer shell is bound by the radii. And the inner shell has a charge of
Welcome
for
to
the electric
EDU
field
World
everywhere
Space.
has a charge of plus 4q. If we can find
The inner shell
where
is
the
bound
charges are
by the
going.
radii
Shell and
and
so
the outer
so
shell
let's go ahead and look
by
at
the
the
radii.
the inner shell has a charge of
Welcome
for
to
the electric
EDU
field
World
everywhere
Space.
has a charge
And
of plus
C,
4q. So in order to find the inner shell, we're going to write down the inner shell and the outer shell. So let's go ahead and the inner shell has a charge of
Welcome to
the electric
EDU
field
World
everywhere
Space.
has a charge of
And
plus
C
4q. So in order to find the inner shell, we're
Welcome
going to
to
write down
EDU World
the inner
Space.
shell and the outer shell. So let's go ahead and the inner shell has a charge of
Welcome to
the electric
EDU
field
World
everywhere
Space.
has a charge of plus 4q.
And
So in order to find the inner shell, we're
Welcome
going
to
to
EDU World Space.
Okay, so the problem is the inner shell and the outer shell.
Welcome to
The
EDU
outer
World
shell
Space.
has a charge.
Welcome to EDU World Space.
Okay, so the problem is the inner shell and the outer shell.
Welcome to EDU
The
World
outer shell
Space.
has a charge.
Welcome to EDU World Space.
Find the shell. The problem is the inner shell and the outer shell.
Welcome to EDU World
Shell
Space.
has a charge.
Welcome to EDU World Space.
Find the shell. The problem is the inner shell and the outer shell.
Welcome to EDU World Space. Welcome to EDU World Space.
case, just a constant, 9 times 10 to the 9. You can also write it by that small, and then also divided by 4 or 5 as well.
Right, so we are given F1.
Okay, so
it's
let's
along
find the
the
electric field.
x-axis.
Alright, so
Force 100.
right at this green spot, we are
Also
on
given
the
F2.
side, this inertia. There is no charge here. If there is no charge, then Q is 0, so the electric field is
Right here. So we have
What about in between our first unit shell, A to B? Well, remember that in a conductor, the total electric field must be 0. So, if there's no charge on the inside, we reduce E must be 0. B less than R less than C, minus first coordinate. Our inner shell has a total charge of plus 2Q, and so that is about to be Q equals 2. So Q is plus 2Q, right? So that means that the electric field can be written as a positive charge in terms of epsilon, or just this case. Writing it like that, we get 1 divided by 4 pi epsilon 0 times the total charge inside, which is 2Q, divided by our solution. And let's see now. C less than R less than D, so now we're in the outer region. Okay. So for these outer regions, I know that the electric field must be equal to 0 here in this region has, because when they're in the electric field, that field must be 0. Plus 2Q here. So we need minus 2Q on this inner surface. But in general,
using
still should be 0 there. Because it works out. And finally, when we are outside of the system, what we have to do is take the total charge minus 2Q plus 2Q minus 2Q. So Q goes to minus 2Q. And we get E equals 1 divided by 4. And 1, let's see now. Times minus 2Q over R. Alright, we can go ahead and graph this. And what do we see? 0, 0. Here, we need minus 2, 0 there. Between B and C, we see 2
process.
four sides. And now we have to remember length properties. So even though that this is a quadratic function, you can get our little graph and see what happens when you have a negative value outside your expression that you're working with. So I'm grabbing
Right here, and that's the projection.
see what happens when you have a negative sign outside of the expression.
So actually now F2 is equal to F2. So projection, we get to now break that up into
It looks like now something that has turned over when you graph it, there will be 2 solutions. Make sure that you choose the physical solution. And so in this instance, it would be something Alright, there we go. Okay, so now we can look at the properties that are around these shells. Okay, let's look at the inner surface of our small. The inner surface of our small. Remember, electric field must be 0. There's nothing on the very inside of this guy where that green dot is. So, this guy must be 0. What about on the outer surface? Outer surface must be the total charge on the shell. It's 2Q. Okay. Let's look at the large one. Okay, on the inner surface, we need to have an electric field of 0, so it has to cancel the total charge on this inner shell. So we need a negative 2q on that inner surface. Okay, so now we can look at the, okay? And then what about on the outer surface? Okay, let's look at on the outer surface, the inner surface of our small, all you have to do, remember electric field must is, think about, okay, well there's minus 2q right here. What has to be on the outer surface?
All components for activity
2q would be the total charge on the shell. 2q. That's the only way for the net charge to be okay. Okay, on the inner surface, we need to have an electric field, so it has to cancel the total charge on the inner shell. So we need a negative 2q on the outer surface. Okay, so and then what about the outer surface?
Welcome to EDU World Space.
Our number here is positive. It's going to be
Okay,
negative.
so we have two concentric shells and a radius A and a radius B of our inner shell, and a radius C and a radius D of our outer shell. The inner shell has a total charge of 2, the outer shell has a total charge of minus 2q, so we're going to find the electric field diagram and where the charge is. Let's get started. So remember that when you have a point charge, the electric field is given by this. Remember what K is? K equals 9 times 10 to the 9. It's also equal to 1 over 4 pi epsilon. Epsilon is just a constant. Also remember Gauss' law. Here it is. It says that the closed loop integral of E dot dA equals Q, the total charge of closed, divided by epsilon. Alright, so, first region, radius less than A. Okay? We are right here in this little green dot. We have no charge there. With no charge, Q is 0, so E must be 0 point charge. Okay, A less than R less than B. We're in this inner shell, first or smaller shell. This is a conductor. What are the properties? It's also equal to 0 inside of the conductor. 1 so pi 0. B less than R less than C. So now we're in this first order division. Well, also remember charge in that region, Q enclosed. Well, just the charge of that inner shell. It's 2Q is the closed. So now we can just imagine that it was a point charge and say that the electric field is Q. Alright, so first region 1 radius divided by 4 pi epsilon. We are right here in this green dot times Q, total charge inside, 2Q over R squared. There it is. Okay, A less than R less than B. Alright, now we're in our outer shell. C less than R less than D. C less than R less than D. Well, if you look out to the surface, we're somewhere in here. What is the total charge in here? Well, it must be 0. Why is that? We're inside of the conductor. So, E equals 0. There it is. Back. Now what happens if we are outside of that? So now what happens if we are doing a Gaussian surface outside of this one? Well, what is the total charge enclosed? Pi epsilon plus 2q minus 2q times equals 0. E must equal 0 here as well. We can go ahead and graph this. 0, 0. So we have these regions of 0 in our outer shell. B to C, right here. C goes something like this. It's 1 over R squared. And then it goes straight back to 0. What is the total charge? Alright, now let's look at where these charges might be located. So, what is the charge on the inner surface of our smaller sphere, of our smaller shell? So, if we are looking at this region right here, what happens if we are outside of it? Well, I know that the electric field must equal 0 here. There's no charge on the inside. There's nothing induced. It needs to equal 0. What about the outer? Plus 2q. Minus go right here. That equals 0. Well, what is our charge enclosed here? Plus 2q. That's everything. Everything is in there. We need an electric field due to plus 2q charge. There it is. And then it goes straight back to 0. Plus 2q. What about our large shell? We go right on this inner diameter, right here. Okay, you know that the electric field must equal 0 here. That means it needs to cancel with this plus 2q that's happening right here. That means all of the minus 2q is going to land at this surface. Minus 2q. Right here. Well, then what about this outer surface? That's 0. We have a net charge of 0 here.
Magnitude of the resultant force is more than its direction.
So, the outer is 2q. Must equal our large we go right on the inner diameter.
So the perpendicular
that means all of the minus 2q is going to land this
Welcome to EDU World Space.
Okay, so for this problem we have an inner shell and an outer shell. And the inner shell has a charge of plus 2q, the outer shell has a charge of plus 4q. The inner shell is bound by the radii A and B, the outer shell is bound by the radii C and D. We're looking for the electric field everywhere and see if we can find where the charges are going and what's happening. So let's go ahead and look for the electric field everywhere. So, in order to find the electric field, we're going to write down Gauss's law, which says that the closed line integral of E dot dA equals total charge that is enclosed in our region divided by epsilon 0. So, in general, this is our Gauss's law. And this is our area element. This is where total charge enclosed in our Gaussian surface. This is epsilon 0, just opposite. And E is what we are. So let's look for our first region, which is when we have a radius less than A. So for r less than A, well, we don't have any charge there, so that means that Q equals 0. Q equals 0, so E equals 0. We're going to write down Gauss's law, which says that the integral between dA equals 0 equals this region. Alright, what about if we are in between A and B somewhere in this shell right here? Well, if it is a conducting shell, then by definition, it must have 0 electric field. So we have the same thing. E is equal to 0 here. Which is when we have the radius So now what about this cavity between B and C? Well, we don't have any charge there. So for B, R, and C, well now we do have some charge. We have a total charge on this shell, plus 2q. So, just in general, we know that the formula for the electric field of a point charge, E, equals, well, K, which is 1 over 4 pi epsilon, or 99, KQ, it must have 0 divided by r squared. So, we have the same thing. We can use this for our region between B and C. And we see that the electric field E equals, now what about this cavity?
And this is one of
K.
them. It's one problem, but there's two parts.
Q,
We've
to
got a 5, 12, 13 triangle.
Q right here is the total charge divided by R squared. R squared
26. And we've got
write
a
this more explicitly.
30 degree
1 divided by 4 pi epsilon
triangle here.
Times 2Q.
And it's 30.
Over 99 squared.
Let's put them.
Okay. Now what about the region C and D? So now we are in this outer ring. Well, we are in this outer ring. Remember that the electric field must equal 0 because it is a conductor field.
Negative.
So, for the region between C, R, T,
30.
E, right here is 0.
Plus, minus.
Okay. And then finally, what about the outside of this object?
30.
So what happens if R is greater than D?
30. So, check.
Well, when R is greater than D, then we have the total charge enclosed, which is 4Q plus 2Q, 6Q. Now, so we just can use this symbol right here for our
So,
zeros,
negative
this point charge,
15.
and we get the field of the E
The cosine of 30 degrees is inverted field
equals 1 divided by 4 pi
check.
C epsilon 0
F2.
T times 6Q
It's negative 26
over R squared.
times 513.
Finally, what about those are all the regions, now we can go and graph
Times
this.
12.
So if we wanted to graph it, it would be this. Here we have R, and
I
we have
simplifying
A,
plus
B,
negative 24
D, and we get
checking the work.
okay, equals. And we are going to get between regions C and B.
That's correct. 26.
And what about between C and D?
So here we are given
Originally,
forces
0 because we have no charge inside of that inner shell. And between regions B and C, here's our total regions. So, because it's 1 over R squared, so something like this. And we see a similar function for when R is greater than D. But this time,
the values that is one
we are going to have a different prefactor in front, and it's going to be a little something like that.
is equal to 20.
And so
With that,
that's
the angles of
that. Now, what about the charges on the
next
inner
here
surface? Originally,
right angle components.
inside.
Values that we see equal.
Okay, so the inner
Based on this, you have to find out the magnitude of the resultant force and its direction.
It has to be 0. Why is that? Because the electric field is 0
You can
on
take
where we have a
the total x component of all the forces. So starting with F1. So F1 is the
this
sign
time,
of
on the charge right there, there's going to be inside, is a
an angle from the vertical to
so
the perpendicular component to
the
the
inner,
plus F2 is also a component to the right. Based on this, you have to find out of
inner is 0.
plus the magnitude of the
Now,
resultant
stop. Okay, what about the outer? All the outer surface right here. So,
Now this is based on this. First of all, let's
it needs to contain all the charge for this inner shell.
plus
So it has to be plus 2Q.
cos of 50 degrees minus F cos
Okay, and what about for our large? Okay. With the inner. So we do a Gaussian surface right here. We know that
This is
we must have a net 0
kilonewton is the
electrical.
total X component. Similarly, Fy will be equal to 1
The only way for that to happen is that there
force
must be an induced negative 2q charge on the inside of here. So it's a negative 2q.
This is vertically downwards.
Why is that? Because we need E net t equals 0. Okay? On the outer surface,
Since values you have to plug in F1
our Gaussian surface.
cos of 40
That's just the total charge of 4 plus 2.
for sine of
Okay.
plus 26 sine alpha is
Also, another thing to note about this graph is that this is, if we were to have units on this, we would expect that this would be taller than this negative 2. Is this is 6 divided by 4 inside? This is 2.
0.49 kilometers. So these are the components.
Of German net.
That means the force will be
And that's
what
that.
is
The outer surface.
I can do it directly. This is 3.8 squared
That's just the total charge.
plus 3.49 squared complete total. So it's coming out to 17.1.
Welcome to EDU World Space.
So this is a net resultant force and angle
This is
organic work and then force y over x.
expect that this would
If y is 3.49,
be taller.
meter equals 16.8
6 divided by 4 inside.
and because of this video value 1.65. Counterclockwise from positive x-axis. So this is the first quadrant. I hope this is clear to you.
So far this section seems to be exactly the same as the previous section. Don't know what is different, seriously. So, we're shown that this is 30 degrees. We're also shown that this down here is 45 degrees. But I would rather mark this as 45 degrees, and it would be 45 degrees because in all it's a right angle. So far this section is the magnitude and direction of the resultant force. Well, don't know what is different, seriously. Force resultant force in the x direction is going to be 430 plus 800 cosine 45. Force resultant in the y direction is going to be 400 sine 30 minus 800 sine 45. The resultant force is going to be the square root of frx squared plus f800y squared, and the angle is going to be the inverse tangent of y over fr is going to be. Let's put all of these into a calculator. It's important that you do the first two so that you know exactly where that theta is, whether it's downward or upward or horizontal. And so, go into a calculator, and the angle is going to be 400 cosine 30 plus 800 cosine 45, 912 the square root. All of these into a calculator. It's important that you do the first two. Okay, next one. 400 sine 30 minus 800 sine 45 negative 366 newtons.
All of these into 400. First two.
Square root. First one. And so, squared. Plus second one. Sine 400 sine squared is 983 newtons. And theta is the inverse tangent of the second one, or the y direction, over the x direction. Squared is negative 22. 21.8 degrees. So we're supposed to measure clockwise from the positive x-axis, so that would be correct. Those two are my answers. Let's check in the book. 983, 21.8. Yeah, it would be positive 20.8 as measured from in the clockwise direction. So again, drawing the diagram and figuring out what it means is most of the battle here. Y, Z, X, and we need to continue the Z axis downward. We're given F1, which appears to have no x component. Well, that's going to be convenient. So it's a 3, 4, 5 triangle, but it's got no x component. Z, X, oops, again, listen, there we go. Okay, F1, F2 has all three components. That's going to be convenient. Z. So it's a 3, 4, 5. But the angles are directly given. F1, which appears to have no x component. Okay, so that's going to be arrows in these. I guess because the book does. And the angle with y is 120. So yeah, they're all directly given. So let's go ahead and do F1. F1 in the x direction is 0. F1 in the y direction is, well, it's going in the positive y direction 3/5 of 450. Well, 45 divided by 5 is 9. 9 times 3 is 27, so that's going to be 270 newtons in the positive direction.
Welcome to EDU World Space.
F1Z is going to be 4/5 of 450, but it's in the negative direction. So that's going to give us negative 360 newtons. So let's move on to F2. This is actually all pretty straightforward. F2 in the y direction is just going to be the 525 times the cosine of x direction is going to be alpha, which is 45. F2y equals 525. Cosine of the y direction one is 120 degrees. And F2z is just going to be 525 cosine of z, which is 60 degrees. So this y one should end up giving us a negative number. The other one should be positive. So let's put them into a calculator. 525 cosine of 45 is 371.2. 525 cosine 120. Negative 262.5 newtons. And 525 cosine 60 is just going to give us 262.5. Okay, so now we have to add them together. Adding the x components, well, there is only one x component. So that's going to be, so I'm going to write it in vector form. 371.2 I F. So now I'm going to do 270 minus 262.5. I don't trust myself, so I'm just going to do it. 270 minus 262.5, 7.5, dot 0. Plus 7.5j, and then in the k direction we've got negative 360 plus 262.5. 262.5. That's going to be, so I'm just going to write 70 minus 262.5 and give us negative 97.5. We need to sketch the vector and find the magnitude of the height. Well, sketching the vector is what I would do next. We've got 371 in the I direction. Then we've got 7.5, which is almost nothing, in the j direction. And then we've got a negative k direction. So it's going to be like down and over there. Maybe something like this. Alright. So now, then we've got 7.5 f sub r square root g71.2 squared plus 7.5 squared plus negative 97.5 squared. And the calculator? J direction. Then we've got a negative. So it's going to be like down over there. Something like this. 384 alpha 371.2 over 384. Beta and gamma are going to be very much the same. inverse cosine. And gamma, very much the same. 371.2 over epsilon. 14.8. I'll just put 7.5 in the numerator. And gamma, very much the same. 9. And negative 97.5. 100. 371.2 over. Now I'll check. 14.8. Inverse cosine. 7.5 in the numerator. 371.2 over 9. Of course, I'll begin by negative 97.5. 14.8. 100. 7.5 in the numerator. Now I'll check if there are 3 forces. 9. And negative 97.5. 3. 100. Verticals. Now I'll check. Negative 97.5. And after 1 that appears to be in the equity plane. Since F1 is in the equity plane, it shows like negative 97.5. Right angles are in there, but that's what they are showing us. So, F1 happens. These are proportions. 4/5 of 9. And that's the dude. Negative 97.5. Of course I can do this.
Welcome to EDU World Space.
So in this question we have been given the state of the screen of your ball, right? So in this we have if direction is equal to 6, x on the y direction is equal to 5, right? And the this rate is equal to negative 650 into 4 6, right? Direction, right? Now we are going to use the
in the negative x direction is negative
Welcome to
right?
EDU World Space.
And for that, you know, it's just to build the circle, and for that we need an extra.
Right, but that I was thinking about.
Right, so we have to see that
F2, what do we get that on
if
F2?
with that
We are given that its projection going to the xy plane.
Right now, all we need to do is that we need to find out the radius of the circle, and we have the expression for the circle for radius as well, right? So we have underneath the thickness of the curvature straight divided by 3 plus divided by 3
I like
half the value just plug that in, and you get that equal to
F2 is xy plane is F2
to 1 into 10 to the power negative 4, right, and that is approximately 3 equals into 10 raised to power negative
Again, I could think a little bit.
right. Now what we need to do is that we draw the circle. Right. So let's take a look at that. So now as you can see over here that this is the point A that with the rate of strain is occurring, right? So we need to measure the angle from this, right? So now the principal strains are easy to find, right? Because you take the head of the circle. Now for that, principal strain is equal to 14 right? So you have the values. So that means that you get that
Sine doesn't matter.
right? And the other principal strain is plus r, right? Again, you have the values, just plug them in,
direction.
and you will have the values that you also in Newton, right? So you get anything
They are both
-6. Right, now that we have this value in this space, we need to find out the maximum in place to strain, right? That is given by this divided by 2 and equal to r. Right, so when you check this thing over here, we can find out the value of maximum influence rate, right? And gamma from maximum influence rate, that is equal to r, and that is equal to principal strain, right? So you have values, just need to plug them in, and you have your value that is 6 times 6. Right, now since the principal strains, they have the same sign, right? So they have the same sign.
Okay, and then
we can directly have the equation for the maximum of the strain.
also
Shear strain, right? That is maximum
200.
surprised
that everything is in the positive direction.
This concludes our solution.
V, X, V. Yep, everything's positive. So, I need to write this in Cartesian vector form.
Welcome to EDU World Space.
So let's go with this question. So in this question we have epsilon A, epsilon x equals square, theta, plus epsilon y minus square, theta, plus 54 gamma xy, theta, by theta. With this epsilon x equals to epsilon y equals to 0. Substituting the value we get gamma xy equals to be 5.7 and this is minus 4 ua equals to y1 path a1 minus y2 path a2. Doing this we get ua as 29.0653. Now we have tau xy s. So let's just see I x silent I x is a tau x e plus epsilon y 5 by s plus 54 by d4 minus d4 to d minus d. So that means tau xy s plus equal to x we get d. Now we have tau xy equals to g.
This diagram looks easier.
This is what 38.997
A little bit harder to
5.6 10 is to power 6 5.7 10 is to power 9 is to P comes out to be 85.05.
Okay. So, continue this through.
Welcome to
We've got a
EDU World
point
Space.
E down here, which looks like the easy one.
So in this question, the
Definitely.
radius is
Point A.
millimeter, right? And the material that is used over here is steel. The tension that is applied over here is of magnitude 3 right? And we are required to determine the strain along the x dash direction and the y dash direction, right? Now, the thing to note over here is that as there is no load
Oh no.
that is being applied over here, right? So it means that if there is no load, so there would be only torsion present. And as there is only torsion present, so it means that there would be no stress. It means the stress in the x direction is equal to stress in the y direction, that is equal to 0, right? And if there is no stress, so it means that there is no normal strain, right?
The hypotenuse is 2 feet.
It means that the strain in the x direction is equal to the strain in the y direction, that is equal to 0, right? So now since this is over here, let's write the strain rosette equation for 45 degrees, right? Strain rosette equation for 45 degrees is, right, set if there is
And
the
this
strain
is
along the
sine.
x direction, as there is only strain along the x direction, cos is cos y, and
Alright, so the distance from A
strain
to
along the y direction, right? Sorry, if there is no stress, strain along the strain along the y direction,
going to be
45
x
plus
direction
gamma
is
of
going
x
1.5.
45 degree and cos 45,
And
right?
the y direction
Now let's discuss that
is going to be
strain
negative
along the x and y direction, right, could be 0, so it exactly equals to
negative 1.
0, right, is liquid system, so solve it and you get that it is equal
In the z direction, it's going down 4 feet.
to positive x, sorry, gamma sum x divided by 2. Right, let's say that this is equation number 1. Now what we need to do is that we need to write the strain of the equation for 135 degree. Now how did we get 135 degree? So 45
Well, in the x direction, it's going backwards, so negative 2 times 1.
right? So now what we need to do is that we need to write
In
the
the
rosette equation,
y
right?
direction,
So we
is
have
over 2
sorry, 135 degree, right?
x direction.
135, 135 is
That would be times 1.
sine 135 degrees. Right, sorry, gamma. So again, these nine terms would become 0 and we get back this term. And solve it and you get that it is equal to negative gamma by 40 by 2. Right, let's move this equation up. Now what we need to do over here is that we are going to use the torsion formula 5.6, right, which is torsion maximum is equal to T times E divided by J, right? And we call that torsion is equal to T times gamma. Now what we're going to do is that we are going to compare these two equations and we will solve it for gamma, right? And when we solve it for gamma, we will get this right expression, right? So what we need to do over here is that we can just plug in the values and we will get that gamma is equal to
FAB, which I did not write down yet, the book tells us that
0.50, right? So plug it back in equation number 1.
it's 20 pounds.
You will get that it is equal to
Going to be
positive and negative 0.05.
vector AB,
That is equal to positive point 0025 and this is negative point
1.5 over the square root.
Right, that is equal to
1.5 squared.
positive point 5, right? So this is your value and you get the gamma is
Okay. That gives me 6.84I.
Welcome to EDU World Space.
-1 into the numerator.
So in this question we are given the velocity of the space at the point that we are studying, right? It's redirecting in the y direction, so you take a 6, right? And it is 650 into 10 raised to power -6, and
C. So now the denominator becomes, well, first of all, FAC is
what we're going to do over here is that we are going to use
40 pounds.
the movers
So it's 40 times.
Welcome to EDU World Space.
circle, right? So in this question, clearly it's going to be of help over here, right? And we are going to take help of the example
-2 sine
6, right? So we can start working on the problem. Now to be able to build a circle, we need the excess, right? So we are going to use 10.13, right? So after that, if we are the actual one and 4c is equal to right? And that is equal to
Alright, so
sum of the
numerator is -2 sine 20.
plug in the values and you get that it's equal to 600
-4.7.
right? Now we also need
I'm going to put the
radius
2
of
plus
the
2
circle,
plus 20 in the
right? And
numerator.
that can be found out by using right? So that is under root the
6.
difference of the space minus by 2 whole square plus
And now -4.
whole square. Right, so again we have all the values, we just need to plug them in and you get that equal to 3.46.
Add those together to get the resultant.
Right, and that is approximately equal to 246 into 10 right, now all we need to do is that we need to draw the graph circle.
I.
What we are going to do
That is 27.6 minus 4.6.
given state of affairs occurs at point A, and we know the angle from that point.
23.
So let's first of all take a look at the circle, right?
18.2 plus 1.8.
Now as you can see over here, right, that the given point of strange, right, they are putting at 93, and this is the radius of the
And we're still not
circle,
done.
right? So this is the like that, right? Now what we need to do over here is that circle principal strains are they are easy to find, right? So we're going to take the help of this closure, right? So principal strain is equal to OC negative R,
That in the
that
calculator.
is 600 negative 3.4 into 10 raised to power negative 6, right? So that is equal to 253.6 into 10 raised to power negative 6, and that is equal to 254 into 10 raised to power negative 6, right? Now we need to find out the other principal strain, so that is equal, and this is equal plus R, right? So 600 plus 346.4 into 10 raised to power negative 6, right? And that is equal to 946.8 into 10 raised to power negative 6, right? To 946 into 10 raised to power negative 6. Right, now what we need to do
Yes,
is
it
that
is.
we need to find out the
And then to get
maximum
alpha, beta, and gamma, we just use the inverse cosine. F bar x, which is 1.97,
right?
over
So
F
for that we
bar,
have
which
an
is
equation that is
1.1.
gamma plus
Not
maximum,
too calculated.
and now we need the aperture, that right? And right, that is divided by 2 and equals R, right? So we are going to simply just shift this to over here, right? And we have a value, so what has gamma, that is
Beta.
is going to
Have to change
be
the
R,
numerator
right?
to
So
23.
right now,
Yes, it is. Gamma, change the numerator to negative 46.
Alright, we can write the difference of the principal streams, right? So you calculate it and you get that equal to 692.6
And those are correct.
right? And that is approximately equal to 693, that is equal to 56. Right, now since the principal streams they have the same sign, right, then the absolute maximum stream would be
This seems like a fairly
absolute
complicated one.
stream,
But, as always, draw the diagrams.
right, and this would be
So,
29.6
we've got
into
F2.
negative 6. So this
Change the numerator to negative 200. We've got F3. This seems like a fairly
right, so
6, as always.
And it's in a 5, 12, 13.
Welcome to EDU World Space.
And
So in this
we've
example, we have an inner shell
F1.
with positive 2Q charge and an outer shell with minus 4Q charge, and we're going to find the electric field everywhere.
5.
So to begin, we need to write down Gauss's law. Clothesline integral, or the closed loop integral of E.dA equals the total charge inside divided by epsilon naught. Also remember that when we have a point charge, we can say that the electric field equals KQ, total charge inside divided by R squared, this way. K is just a constant, 9 times 10 to the 9. You can also write it in terms of epsilon, and that is equal to 9 divided by 4 pi epsilon naught.
That's results.
Okay, so let's find the electric field. Alright, so right at this green spot, we are on the inside of this inner shell. There is no charge here. If there is no charge, then it will be 0, so the electric field is also
All of them.
to
It's going to be
0.
F1 sine.
So to begin, we need to write down what about in between our first shell, A to B. Well, remember that in a conductor, the total electric field must be 0. So if there's no charge on the inside, then the reduced E must also be inside divided by R squared.
X direction.
B less than R less than C, we're in this first ordered region. Our inner shell
Let me simplify that.
has a total charge of plus 2Q, and so that is what would be Q enclosed here. So Q enclosed
260
is plus
divided by
2Q.
13.
So that means that the electric field can be written as a point charge in terms of epsilon or just as K. Writing it like that, we get 1 divided by 4 pi epsilon 0 times the total charge inside, which is 2Q, divided by R squared.
Minus 260.
And let's see now. C less than R less than D, so now we're in this outer region. Okay, less than R less than C. So if we're in this outer region, I know that the electric field must be equal to 0.
26 divided by
Because when we're inside the conductor, the electric field must be 0 at plus 2Q here. So I need minus 2Q on this inner surface. But in general, E still must be equal to 0 there because we are inside the conductor. And finally, when we are outside the system, all we have to do is take the total charge minus 4Q plus 2Q is minus 2Q. So Q is minus 2Q. And we get E equals 1 divided by epsilon times minus 2Q over R. Alright, we can go ahead and graph this. And what do we see? 0, 0. So we need a minus 2 0 here. 0 there, but in general, between B and C, and C is 2, and finally we are outside 4 pi epsilon 0 also, like this, all you have to do is
Want that
and now, you have to remember many properties, so even though that this is a quadratic function, you can get out your graphing calculator
now also
and see what happens when you
want
have a
inverse
negative
tangent
value outside
f1 cosine 1 pi minus 2
your expression that you're working with.
over f1
So I'm graphing it out, and I think that all of you should graph it as well.
100
To
b
see what happens when you have a negative sign outside of the expression.
I'm going to put both of those into a graphing calculator.
It looks like
Desmos.com.
something like this.
In here, in Desmos, I'm going to that
Get out your
b by
and more
and
when you graph it, there will be two solutions. Make sure that you choose the physical solution. And so, in this instance, it will be simply
square root.
your expression.
F1 here, y.
Alright, here we go. Okay, so now we can look at the charges that are around these shells.
Minus 240.
Okay, let's look at the inner surface of our small. The inner surface of our small.
Y sine.
Remember, electric field must be 0, and on the very inside of this guy, where that green dot is. So, this guy must be 0. What about on the outer surface? Outer surface must be the total charge on the shell. It's 2Q. When you graph it, there will be two solutions.
Y value, which
Okay,
is y
let's look at the large one.
minus y.
Okay, on the inner surface, we need to have an electric field of 0, so it has to cancel the total charge from this inner shell. So we need a negative 2Q from that inner surface. Okay,
Now
so
let's think about what this happens to be.
okay,
5
and then what about on the outer surface? Let's look at the inner surface of our small. The inner
between 0
the
and
outer
9.
surface, remember what all it has to do
Force
inside is, think about, okay, so well, there's minus 2Q right here, but on the outer surface, what has to be out there?
So I'm gonna scale my
Minus 2Q. That's the only way for the net charge to be like this. Okay, on the inner surface, we need to have charge minus 2, it has to cancel.
and I'm gonna scale my y-axis from 0 to like
Negative
5.
2Q. Okay, so and then what about
0 to
Welcome to EDU World Space.
I see a point of
okay,
intersection.
so we have here two concentric square shells in a radius A, a radius B of our inner shell, and a radius C, a radius C of our outer shell. The inner shell has a total charge of plus 2Q, the outer shell has a total charge of minus 2Q, and we're going to find the electric field everywhere
10.9 degrees.
where the charges are. Let's get started. So remember that when you have a point charge, the electric field is given by this. Remember what K is? K equals 9 times 10 to the 9.
No answer.
It's also equal to 1 over 4 pi epsilon.
Welcome to EDU World Space.
Epsilon is just a constant. Also remember Gauss' law. Here it is.
But I don't
Gauss. It says that the closed loop integral of E dot dA equals Q, the total charge of closed divided by epsilon. Alright, so, first region, radius less than A. Okay? We are right here in this little green dot. We have no charge there. With no charge, Q is 0, so E needs to be 0. It's given by this. Remember, Okay, A less than R less than B. We're in this inner shell first, our smaller shell. This is a conductor. One of the properties is that it uses
XY component of the force.
B less than R less than C. So now we're in this first one. Also remember, well, what is the total charge in that region? Q enclosed. Well,
Angle is the third
charge
degree.
in your shell. It's 2Q.
So
Now we can just imagine that it's one charge and say that the electric field region E equals
30.
1 divided by 4 pi epsilon times Q, total charge inside, 2Q over R squared. There it is.
Calculator here. 7 over
Alright, now we're in our outer shell. C less than R less than D. C less than R less than D. Well, do our Gaussian surface or somewhere here.
Now,
What is the total charge in here? Well, it must be
Direction.
zero. Why is that? We're inside of the conductor.
that's not going to be as
So,
easy. But the first thing that I noticed is looking from above.
now we're going to do that. Now what happens if we are outside of this?
X,
So now what happens if we are doing a Gaussian surface outside of this system? Well, what is the total charge enclosed? Plus 2Q minus 2Q. That equals 0.
and we can envision
0 here as well.
triangle here.
We can go ahead and graph this.
And so,
0, 0. So we have these regions of 0. B to C, right here. Okay, something like this. That's 1 over R squared. And then it goes straight back to 0.
7 times
Alright, now let's look at where these charges might be located. So, what is the charge on the inner surface of our smaller sphere? Our smaller shell. So, if we are looking at this region right here, well, we have the electric field must equal 0 here. There's no charge on the inside. Here's something induced. It must equal minus the outer. Go right here. Well, what is our charge enclosed here?
over 7.
Plus 2Q.
7
Everything's in the B to C.
30.
An electric field due to a plus 2Q charge. And then it goes straight back to 0.
It's also, that's
Plus 2Q. Right? Now let's look at all these charges. What about our large shell? We go right on this inner diameter. Right here.
beta.
Okay, we know that the electric field must equal 0 here. That means it needs to cancel minus plus 2Q, like this happening right here. That means all of the minus 2Q is going to land in this surface.
So,
Minus 2Q.
from the first equation, I can get alpha.
Then what about this outer surface? It's got to be 0. Plus 2Q. We have a net charge of 0 here.
7 over F is 40.
So, the outer is 2Q.
So, beta minus 4 this side, 7 over F, 5. And gamma is this side, of 7 over F, tangent 30. So, from the first, I can put all of these into the calculator, understanding that F is equal to
Welcome to
0.8.
EDU World Space.
Okay, so for this problem we have an inner shell and an outer shell. And the inner shell has a charge of plus 2Q, the outer shell has a charge of plus 4Q. The inner shell is bound by the radii A and B. The outer shell is bound by the radii C and D. We're looking for the electric field everywhere and see if we can find where the charges are going.
No, put in the
So let's go ahead and
sign.
look for the electric field everywhere. So, in order to find the electric field, we're going to write down Gauss's law, which says that the closed line integral of mu dot
7 over
dA
F
equals total charge that is enclosed in our region divided by epsilon 0.
Now, this one
So
is not
in general, this is our galaxy
look at
and this is our area element. This is our total charge enclosed on the galaxy surface. This is epsilon 0.
and we're going to try to draw it.
So let's look for our first region, which is when we have a radius less than A. So for or less than A, well, we don't have any charge there, so that means that Q is 0.
The angle
0 and our P is 0.
beta in this
Which
angle,
says
not this angle.
equals 0.
And so we really figured out
This region.
180.
Alright, what about if we were in between A and B, so now we're in the shell? Well, if it is a conducting shell, then by definition, it must have 0 electric field.
Beta really is 180 minus 50.
So we have the same thing. E must equal 0, which is the radius less than
123.8.
Now what about this cavity between B and C? So,
Check
for 0, B
the
equals
answers here. This is
CR
2.
C. Well, now we do have some charge. The total charge on this shell plus 2Q. So, just in general, we know that the formula for the electric field of the point charge
I like these two-part problems.
K, which is 1 over 4 epsilon for 99. K is Q,
You've got a 5, 8, 13 triangle.
divided by R squared, same thing.
26.
We can use this for our region
And
when
we've got a
then we
30
see the
degree
field. Now what about this equals
angle here.
K, Q,
And it's
2,
30.
Q right here is the total charge divided by R squared. R squared
Into Cartesian vector form.
just in general. We can write this more explicitly. Divided by 4 pi
So,
epsilon.
F1 is negative
K, which is 1 over 2 is 2Q.
30.
Is R squared. Okay.
Sine
Now what about the
30
region
degrees.
C and D? So now we are in this outer ring.
Plus,
This.
nope,
Well,
minus.
we are in this outer ring. Remember that the
direction's
electric
also
field
minus.
must be 0 because it is a
30.
conductor.
Negative cosine.
So, for the region between
J.
C less than R
The
plus
sine
D, Q right here is E equals 0. R squared
of 30 degrees is 1 half. So,
and then
negative
finally, what about
30
if we
times
are
1 half is
outside
15.
of this object? So what happens if R is
The cosine of 30
D?
negative square root of 3 over 2, so that would be
Well, when R is greater than D, then we have the total charge which is 4Q plus 2Q, 6Q. So
It's
we just
negative
use this formula right
26
here for our regular points charge,
times 5
and we
times
get our electric field E equals 1
26
divided by 4 pi C
times 12, 13
epsilon
times
0 times 6Q
negative pi, simplifying, plus
finally, what about
24.
And checking those are all of our regions. Now we can go ahead and graph these. All in R is greater than D. So if we wanted to graph it, it would be something like this. We have R and E. So we just, and we have
I'm going to treat this as a continuation of number 56. And how I'm going to do that is I'm going to first of all retain most of my work, but I'm going to delete basically all this green stuff here at the bottom.
times 60. And what about the term CD?
We're going to treat this as a continuation of number 50. Okay, got that.
Originally,
Now,
charge is inside the first shell.
we want
C,
the resultant to be a minimum,
because it's a 1 over r squared,
and we want phi
so something like this, and
to be 30
we see a
degrees.
similar function for the
So I'm just going to put it in there
this time,
and look for where
we're going to have
F1
prefactor.
is a minimum.
And it's going to be
Going to a graphing calculator. I wish I could show it to you, but I slowed down my computer way too much.
and so that
So I'm going to write y equals
now
the
what
square
about the
root.
charges on the inner surface?
And look for F1. Well, F1 is going to be F. Cosine of 30 minus 240. So I'm going to write squared plus F1, which is x, sine of 30
We have a Gaussian
plus 300
this
squared. That gives me a graph. I'm going to zoom out here until I can see it.
inner.
I was zooming way in. I want this to be a minimum. The minimum is at
Okay, we've got the other
1 equals 57.8.
surface right here.
Way
Needs to contain all the charge for this inner shell. So this has to keep
and the resultant is going to be the y value on my graph,
about
380. That gives me 7.8. Zoom out here so I can see it. Just a number of digits, 7. Yeah, 380. I want this to be exactly what is the resultant. The minimum is going to be the y value. Alright, we're doing the same problem again. I retained the drawing and the general information, but now we're just told a different value for alpha 3. Alright, we're doing the same problem again. Beta 3 and gamma 3. But now we're just told a different. So, F3x is just going to be F3, which is the 800. We're doing the same problem again. And 120.
This is information we would have done. We're just told expect beta value follows to be F3, which is the 800.
60. Okay. So now we just have to add them all together. Beta. So, is just going to be F3, which is 800. F1x is 350 root 3. Okay.
Welcome to EDU World Space.
Add them all together.
This is
FRY is 800 plus the y direction. 350 is 350 root 3 plus 48. Okay. So now we just have to add them all together. FRY is Z direction, Y direction, 350, 360. F1x is 350 root 3.
Welcome to EDU Workspace.
Z direction. So I'm going to put those into calculator. 350. Okay. There we go. 800 cosine 120 plus 350 root 3 is into squared plus 800 cosine 45 plus 350 plus 480 cosine squared plus parentheses 800 cosine 60, which would just be 400 by the way, plus 360 800 cosine squared 1,600 newtons. I mean pounds. And let's check if that's correct. Yep. Alpha is going to be cosine of FRX over XR. So just putting that into a calculator. For X plus 360 for FR is going to be 1,600 cosine of 82.6 degrees. Then beta, putting in the numerator 800 cosine 45 plus 350 plus 480. That is going to be gamma is 1.7. So checking the answer. Time required. 82.6 degrees. Checking the answer. 800 cosine 45 plus 350 plus 480.
What if you want to get the signal to microwave the moon and back? How long would that take? Time is here. This is a total time to the moon and back.
Welcome to EDU World Space.
So in this example, we have an inner shell of positive 2Q charge and an outer shell of minus 4Q charge, and we're going to find the electric field everywhere. So to begin, we need to write down Gauss's law. Clothesline integral, closed loop integral of E dot dA equals the total charge inside divided by epsilon naught. Also remember that when we have a one charge, we can say that the electric field equals KQ, total charge inside, divided by R squared, distance by K is just a constant, 9 times 10 to the 9. You can also write it in terms of epsilon, when it is equal to 1 divided by 4 pi epsilon naught. Okay, so let's find the electric field. Alright, so right if this brings about on the inside of this inner shell, there is no charge here. If there is no charge, then Q is 0, so the electric field must pass the outer shell equal to 0, and we're going to find out. So to begin, we need to put about in between our first shell, A to B. Now remember that in a conductor, the total electric field must be 0. So if there's no charge on the inside, then the induced EMF must be 0. B less than R less than C, we're in this first ordered region. Our inner shell has a total charge of plus 2Q, and so that is what will be Q enclosed. So Q enclosed is plus 2Q. So that means that the electric field can be written as a charge in terms of epsilon or distance. Writing it like that, we get 1 divided by 4 pi epsilon 0 times the total charge inside, which is 2Q, divided by R squared. And let's see now. C less than R less than D, so now we're in this outer region. K less than R less than C. So if we're in this outer region, I know that the electric field must be equal to 0 here in this region. Because when we're inside the conductor, the electric field must be 0. So plus 2Q here. So we need minus 2Q on this inner surface. But in general, E still must be 0 there, because we are inside the conductor. And finally, when we are outside of the system, all we have to do is take the total charge minus 2Q is minus 2Q, so Q enclosed is minus 2Q, and we get E equals 1 divided by epsilon times minus 2Q over R squared. Alright, we can go ahead and graph this. And what do we see? 0 is here, 0 there, but in general, between B and C, we see 2, and finally we are outside 4 pi epsilon 0 R squared, like this. And now, you have to remember one of the properties, so even though this is a quadratic function, you can get out your graphing calculator and see what happens when you have a negative value
that
outside
2,000 hertz is
of
the resonant
your expression that you're
frequency.
So
I guess they did that because omega 0
see what happens when you have a negative sign outside of the
is
expression.
1 over the square root of L times Z resonant frequency. And so, I guess they did that because 2,000, or rather 2 pi times 2,000 omega 0.
When you graph it, there will be two solutions. Make sure that you choose the physical solution. And so, in this instance, it will be simply your expression.
So, omega 0 L
Alright,
is
here we
1,034.
go. Okay, so now we can look at the charges that are
And by the way, omega 0
around these
is
shells. Okay,
valves.
let's look at the inner surface of our small. The inner surface of our
Omega
small.
times L.
Remember, electric field must be zero. There's nothing on the very inside of this guy where that green dot is. So, this guy must be zero.
Okay, good.
What about on the outer surface? Outer surface must be the total charge on the shell. Okay, this will be the large one. Okay, on the inner surface, we need to have an electric field zero, so it has to cancel the total charge from this inner shell. So we need a negative 2Q on that inner surface. Okay, so now we can okay, and then what about on the outer surface?
Dividing it by
The inner surface. The outer surface. Think valve. Okay. So there's minus 2Q right here. And then on the outer surface, well, it has to be out there. It must be the total charge.
divided by 2
2Q.
and 5.
That's the only way for the net charge to work. Okay, on the inner surface, we need to have minus 2. It has to cancel the total charge from the inner surface. So we need negative 2Q.
The 18 and 4 divided by 2 here.
And then
And now that's B2 is
Welcome to EDU World Space.
Okay, so we have two concentric shells, and a radius A, out of radius B of our inner shell, and a radius C, out of radius D of the outer shell. The only way the inner shell has a total charge plus 2Q, the outer shell has a total charge of minus 2Q. We're going to find the electric field everywhere, and where the charge is going to be. Let's get started.
okay.
So remember
Looking at that
when you
capacitance
have a
value,
point charge, the electric field is given by this. Remember what K is? K
49
equals 9
farads.
times 10 to the 9.
Sure they got that right.
It's also equal to 1 over 4 pi epsilon.
Welcome to EDU World Space.
Epsilon is just a constant.
XC is 1 over omega.
Also remember Gauss law.
1 over 2 pi FC.
Gauss says that the closed loop integral of E dot dA equals Q, the total charge of closed divided by epsilon. Alright, so first region, radius less than A.
Okay, that
Okay?
was good.
We are right here in this little green dot. We have no charge there. With no charge, Q is 0, so E used to be 0. Okay, A less than R less than B. We're in this inner shell first, our smaller shell. This is it's also a conductor. One of the properties is that E equals 0 inside of the conductor. So, let's do 0 is just X. B less than R less than C. So now we're in this region. Also remember Gauss law. Well, what is the total charge in that region? Q closed Well, since just the charge is out of the shell, it's just dA. So now we can just imagine that it was a point charge and say that the electric field region E equals 1 divided by 4 pi epsilon times Q, total charge and size, 2Q over R squared. Okay, there it is. Alright, now we're in our outer shell. C less than or less than D. C less than or less than D. Well, do our Gaussian surface. We'll send it over here. What is the total charge in here? Well, it must be 0. Why is that? We're inside of the conductor.
XL.
So, E equals 0. There it is. So, now let's do that. Now what happens if we are outside of everything? So now what happens if we are doing a Gaussian surface outside of this system? Well, what is the total charge in pairs? Plus 2Q minus 2Q, that equals 0. E plus 2 equals 0, there it is. We can go ahead and graph this. 0, 0, so all of these functions of 0. B to C, go something like this, it's 1 over squared, and then it goes straight back to 0.
XL and XC have.
Alright, now let's look at where these charges might be located. So, what is the charge on the inner surface of our smaller sphere, our smaller shell? So, if we are looking at this region right here, well, I know that the electric field must equal 0 here. There's no charge on the inside here, so it's going to induce times 2.
Now, since I use the S4 button, anything here that's highlighted in yellow.
Well, what is our charge enclosed here? That's 2Q. It's everything. Everything is on speed.
Whereas all the rest of them are
the electric field due to a plus 2Q charge.
Change for each of them. There we go. Now I need another
2Q.
This one.
What about our large shell? We go right on this inner diameter.
And this 90 to the left.
Okay, we know that the electric field must equal 0 here. That means it needs to cancel with this plus 2Q. What's happening right here? That means all of the minus 2Q is going to land at this level.
I should get 1884,
Minus 2Q.
and 40, which I did.
Then what about this outer surface? It's back to 0. We have a net charge of 0 here.
So now, by the way, this is on the same set of axes. I put 2000 in.
So, the outer
All of these are functional. So,
must equal
all of these is functional. Well, that should be easy. I want it to be a scatter plot, so these values here are not evenly spaced. So I'm going to insert chart. There we go. That's not a scatter plot. There we go. So set up. I don't want line chart. I want scatter. I want it to be a scatter plot. There we go.
Welcome to EDU World Space.
Okay, so for this problem we have an inner shell and an outer shell, and the inner shell has a charge of plus 2Q, the outer shell has a charge of plus 4Q. The inner shell is bound by the radii A and B, the outer shell is bound by the radii C and D. So we can put the electric field everywhere and see if we can find where the charges are going. So let's go ahead and look for the electric field everywhere. So, in order to find the electric field, we're going to write down Gauss's law, which says that the closed line integral of E dot dA equals the total charge that is enclosed in our region divided by epsilon 0. So, in general, this is our Gauss's law. We have an inner shell and an And this is our area element, and this is our total charge enclosed in our Gaussian surface. This is on 0 just across the board. And E is what we're looking for. So let's look for our first region, which is going to have a radius less than A. So for R less than A, well, we don't have any charge there, so that means that Q equals 0.
Let's go back
0,
to the little line
equals 0. So, in order to find the electric field, we're going to write down Gauss's law.
Is there a
So E equals 0. Alright, what about if we are in between A and B, so we're in the shell? Well, if it is a conducting shell, then by definition, it must have 0 electric field.
This almost looks like a straight line.
So we have the same thing. E must equal 0 here.
I think this will work. So apparently, when Google puts in a line chart, the line chart is not
Now what about this cavity
just
between B and C?
a
So for A, B
just line graph.
less than R, less than C.
Input number.
Well, now we do have some
C is
charges.
good.
The total charge on this shell
So now I
is
have.
2Q.
I think this will work.
So, just in general, we know that the formula for the electric field of the point charge E,
As a function of the natural logarithm.
K, which is 1 over 4 pi epsilon, 99, KQ, by definition,
What I'm gonna
divided by
do
R
then
squared has 0.
is like a straight line.
We can use this
I'm going
for our
to
region
move this over
between
more.
C and B, C, that the electric field E
I'm gonna copy
equals
this.
K. Now what about Q?
Now I'm gonna
To
put the logarithm.
Q right here is the total charge divided by R squared. R squared C is just
Drag it down.
we write this more explicitly. 1 divided by 4 pi epsilon. Just in general, we know that the formula for the electric field comes to Q
As a function of the
over
I know that changed everything over here.
Now what about the region C and D? So now we are in this
Okay,
outer
so how am I going?
Well, we are in this outer ring. Remember that the electric field must equal 0 because it is a conductor.
Now I need to make it refer to A.
So, for the region between C
probably change my chart.
D, E equals 0.
We're not gonna do. Okay, so
Okay, and finally, what about if we are outside of this object? So what happens if R is greater than D? Well, when R is greater than D, then we have the total charge enclosed, which is 4Q plus 2Q, 6Q.
This shouldn't change.
So we just use this formula right here for our lower region
Now I can
point charge, and we get our electric field E, well, equals field 1 divided by 4 pi, so epsilon 0 times 6Q D over R squared E. There we go. Okay. And finally, what about those are all of our regions. Now we can go ahead and graph this.
Okay.
So if we wanted to graph it, it looks something like this. We have R, we
I was
have
wondering
E,
if I set my axis
and we have 2Q, B.
the middle change.
So we'll just
The middle is
use this formula right here.
I bet it's going to be symmetric. If I set my center point
And we are going to get between regions A and B.
I'm going to set my x-axis.
And what about between C and D? Epsilon 0.
Horizontal axis.
Originally, 0 because we have no charge inside that inner shell. And between regions B and C, here's our formula. So it goes as one of our squares.
We're not going to see everything, right?
This and we see a similar function for when r is greater than d. But this time we are going to have a different prefactor at the front, and it's going to be a little stupid.
6.6.
And so that's that.
And so you can see that this yellow line of impedance is symmetric, and the capacitive resistance and the inductive resistance are mirror images of each other.
Okay, so the inner surface, we're going to try on the inner surface of the solution. Well, it has to be 0. Why is that? Because the electric field is 0 when we have a Gaussian surface. So this guy, you see a similar definition, there's a charge right there, there's a charge on the inside, and this time, we're going to have the inner, inner is 0. Okay, what about the outer? Oh, the outer surface right here. It needs to contain all the charge for this inner shell. So that's too cute. Okay. And what about for our large? Okay, the inner. So we do have some surface right here. We know that we must have enough 0 electric field. The only way for that to happen is that there must be an induced negative 2q charge in the inside of it. So it has to be negative 2q charge. Why is that? Because we need E net to equal 0. Okay? Now the outer surface, our Gaussian surface. That's just the total charge, 4 plus 2. Also, another thing to know about this graph is that this is, if we were to have units on this, we would expect that this would be taller than this. Because this is 6 divided by 4 and pi. This is 2. Of checking. And that's that. That's just the total charge.
Welcome to EDU World Space.
Also, another thing to remember is that this is, if we were to have units on this, we would expect that this would be taller than this. 6 divided by 4 and
Welcome to EDU World Space.
Well, there is something positive, and these are again, why one, why two, why three, right? And by something value, why? From 70 degrees are 50.5, sine 80 degrees plus 7 plus sine 165 is I direction plus 12 sine 17 minus 50.5 sine 80 degrees plus 17 sine 17 times sine 160 degrees and z direction by something minus and this whole expression is equal to minus 1.88 I plus 1.8 z direction. Now we can also find out the magnitude, the amplitude is equal to magnitude of phi, which is equal to square root of minus 1.8 whole square plus 1.83 plus 1.83 whole square, and therefore amplitude A is equal to 9.36 centimeters, and phi is equal to 1.83 divided by minus 9.8, which is equal to 168.7 degrees.
Welcome to homework.
Because we're supposed to use technology for this, I'm going to use Desmos.com. And my equation for power is 1 half times delta V max squared. Delta V max squared was just 1. Oh wait, no, we're given RMS. So I don't want the 1 half. I just want E RMS squared. We're supposed to use technology. 1 squared. Use Desmos.com. And my equation over Z squared is 1 half. Z is the square root of R squared. R is 1. Delta V max squared.
Welcome to homework.
Because we're supposed to use technology for this, I'm going to use 2 RMS. And I don't want the 1 half. F, but F I'm going to make S. 2 pi F, 1 squared, times L. L is 0.001 over Z 1 millihenry, just 1. Z is the square root of minus 1 over 2 pi F RMS squared. This is 1 nanofarad, so that's going to be 1 times 10 to the negative 9 over Z squared. There. 1 over omega C. Square that all on. 0.001. Alright, we're supposed to make a Oh wait, I'm not doing that. So that would be Emax squared over Z squared, and then I have to multiply by R. R is also 1. So I guess I am 1. Okay, so I'm making a graph of that. 0.001. Zoom out here. 1 over minus 1 over square root of I'm going to change my axis. My y-axis, I'm just going to go from 0 to 1. Okay, so I'm making a graph of that. Okay. Why don't I see anything?
Welcome to EDU World Space.
There we go. So it does go from 0 to 1. The power goes from 0 to 1. 0 almost all the time, but we have a peak at 159,000 hertz. And I want to verify that the width of the resonance peak for half the maximum. So if I want to do that, half the maximum, when the maximum is 1, well then all I have to do is subtract half of that off. Okay? And I can look for the x-intercept right here. They're at 159,292. And 159,017. Equal sign is 275. And the difference is width. So I'm supposed to verify that the width is R over 2 pi L. So let's just do that. R was 1 over 2 pi L was 0.001. Oh no. R over 2 pi L, what it said. So this was R over 2 pi L, full width,
touch the origin, so the
Alright, I do see a mistake here, so it was Z squared in the denominator, so I need to get rid of the square root. I just put Z in the denominator. That's going to be Z squared. Now let's not take out this 0.5. Zoom back. You'll see it's still up to 1. The max is still 1. And now I'm going to subtract half off. And now, let's zoom in and see what we've got now. It's 159,235. No, 159,235. I just put 3 in there. That's minus 159,075. Yay! And I look at that, and now I got the same answer. 160, 169. So,
Welcome to EDU World Space.
welcome to home. you have to draw circles and circles. Throughout the mass circle, you have to determine the center and the radiation by the circle is the horizontal. This will be then next time we have to determine the outflow from experiments of the circle, which will become
Welcome to EDU World Space.
For the new clockwise from the original plane. In more circle, it will be taking 360 degree, we get experiment equals to 60 degree from clockwise to original origins equals to 3 added how to equals to 8 divided by delta v by delta v delta v out is equal to 1 by 2 total displays minus 8 mean from GRC get XLV equal to 8 which is the same equation. So that will be is XL minus XC can also be written as XL minus XC equals to 1 by omega 1 C minus omega 1 N. Now we can write two equations. One of these different frequencies, so you can write that A to B is equal to XL minus C equals to A to C equals to 1 by 2 by F1 multiplied by C minus 2 by F1 multiplied by second equation can be written as so let's define resistance 1 by 2 by F2 multiplied by resistance minus 2 by F3 multiplied by we can rearrange the first equation from the previous case to the value C equals to M by cos that F1 A to the omega plus 2 by F1 plus 2 is like this. So this is the property of the problem right. Substituting the coordinate C this equation we get A to the C that is equals to 2 by F1 A to the C plus 2 by F1 that is L divided by 2 by F1 minus 2 by F2 that is L. Then here for the rearrangement of terms we get A to the C equals to and so we can write the value of L as one here after rearranging L will be equals to A to the C F1 minus F1 minus F2 and L2 divided by 2 by F2 square minus F2 square. Substituting values we get L equals to A minus because is 1 minus F1 is 200 and F2 is 400, 4000 F2 again 4000 divided by 2 by right 4000 square minus 200 square L will be subtract here after squaring we get L equals to 5.8 multiplied by 10 to the power minus 4 Henry, or we can say that L equals to 580 microhenry. So this is the one point L equals to this is the value these are the answers. So the part B of the problem we can calculate value of C from this equation to substitute the value of L and F here. So we get C equals to 1 by F2 by multiplied by F1 is 200 bracket A to the plus 2 pi is multiplied by
Welcome to EDU World Space.
So in this question we have been given the state of strain that we are studying, right? So in this V strain equal on the x direction is equal to 3 and resistance is 1 negative 6. acting on the y direction is equal to 550 into 10 raised to 1 negative 6, right? And the shear strain is equal to negative 650 into 10 raised to 1 negative 6, right? And strain density z direction is 0 because there is friction that is acting in the direction, right? Now we are going to use the Mohr's circle theory, right? And for that we are going to build a circle, and for that we need an axis. So in this question we have written right? So we have OC that is equal to the square value of the base, right? So that is sum of the base divided by 2, right? And you can calculate it together is equal to 4 into 5 into 10 to 1 negative 6. Right now all we need to do is that we need to find out the radius of the circle, and we have the expression for the circle for radius as well, right? So we have under root the strains divided by 2 whole square plus the shear strain divided by 2 whole square. You have the value and plug them in, and you get that is equal to 3.438. That is equal to 1 into 10 raised to power negative 4. That is approximately equal to 348.2 into 10 raised to power negative 6. Right, now what we need to do is to do that we need to draw the circle. Right, so let's take now all we need to do is that we need to find the radius of the circle, and we have the expression for the circle for radius as well. So now as you can see over here that this is the point A at which the rate of strain is occurring, right? So we need to measure the angle from this point, right? So now the principal strains are easy to find, right? Because we'll take the help of the circle. Now for that, principal strain is equal to 1 over c negative r, right? So you have the values, you just plug them in, and you get that is equal to 67.8 into 10 raised to 1 negative 6, right? And the other principal strain is that OC plus R, right? Again, you have the values, just plug them in, and you will have your values, your answer in no time, right? So we have 773 into 10 raised to power negative 6. Right, now that we have this value of the principal strain, we need to find out the maximum strain in plane shear strain, right? That is given by this divided by 2, that's equal to r, right? So when we shift this to over here, we can easily find out the value of the maximum in plane shear strain, right? So gamma maximum in plane, that is equal to 2, and that is equal to the distance of the principal strains, right? So you have values, you just need to plug them in, and you'll have your value, that is 6 times 6 into 10 raised to power 6. Right, now since the principal strains they have the same sign, right? They have the same sign. So same sign means that we can directly have the expression for the maximum value of strain, a shear strain, right? That is maximum strain that's equal to 3 plus 10 negative 6. This concludes our solution.
Welcome to EDU World Space.
So let's solve this question. So in this question we have epsilon a equals to epsilon x into square theta plus epsilon y into minus square theta plus gamma xy theta sin theta. Following this, epsilon x equals to epsilon y equals to 0. Substituting the value, we get gamma xy equals to be 5.7. That is for minus 4 to a equals to y1 bar a1 minus y2 bar a2. Doing this, we get a as 0.0653. Now we have tau xy as plus b
Welcome to
a
EDU World
by
Space.
I x b by I x. So let's tau y we have tau a by 64 here theta plus epsilon d4 minus d4 here theta minus d. So that means tau xy s plus 90.82. Now we have epsilon y. Now we have tau xy equals to g xy gamma xy. So this is what 38.997 into 3 equals to 5.6. 10 to the power 6 and 5 to 7 10 to the power minus 6. B comes out to be 83.055 s plus b by I x by I x. So let's now by 5
Welcome to EDU World Space.
So in this question, the radius is equal to 15 millimeter, right? And the material that is used over here is steel. The tension that is applied over here is of magnitude 2 kilonewton-meter, right? And we are required to determine the strain along the x-dash direction and the y-dash direction, right? Now, the thing to note over here is that as there is no load that is being applied over here, right? So it means that if there is no load, so there would be only torsion present. And as there is only torsion present, so it means that there would be no stresses. It means the stress in the x direction is equal to the stress in the y direction, and that is equal to 0, right? And if there is no stress, so it means that there is no normal strain, right? So it means that the strain in the x direction is equal to the strain in the y direction, that is 0, right? So now since this is all cleared up, let's write the strain Rosette equation for 45 degree, right? Now strain Rosette equation for 45 degree is the strain along the x-dash direction is here, right? Strain along the x-direction for 45, as there is only torsion present, so strain along the y direction, it means the strain in the x-direction.
This question is asking us about voltage and given frequency. So, we're going to go ahead and write delta V is 100 volts. So delta V max
So solve it and you
volts. Then it continues with the sign omega t. There's
sorry, gamma of x minus y. Right, let's say that this is equation number 1. Now what we need to do is that we need to write the strain Rosette equation for 135 degree. Now how did we get the 45 degree? So 45
and a resistor. This question is
right,
then it continues with
now
the
what we need to do
sign. So
is
we
that
need
write the
the
Rosette equation for 45
so
degree.
basically A is just asking us about the resonance frequency. If it's at resonance frequency, then all those powers resist. So omega 0 is
Right.
square root
So again,
1 over LC.
become 0 and only different.
So just putting that into a calculator.
That it is equal to negative gamma by
1 square root.
Alright,
1 over 2 times A is just
now what we
asking
need to
about
do over
the
here is
resonance
that
frequency.
we are going to use the
It's at
torsion
resonance
formula
frequency, negative 6 power, which by the way, that's the same as resist. So
torsion
negative negative power
times
is
divided by G,
square
right?
root
And we call that the torsion is
LC,
equal to
224. So just
what
putting
we're going to do is that
that
we are
into a
going to
calculator.
compare these two equations and we will solve it for gamma, right? And if we solve it for gamma, we will get the expression, right? So what we're going to do over here is that we will just plug in the values and we'll get that gamma is equal to
10 power is negative 6 power, which by the way, that's the same as resist. Just putting that
by
into a calculator.
right? So
Power
plug it back in equation 1 is that it is equal to
is the same as so just putting that
positive
into a calculator.
That is equal to positive 0.6 and this is
So I'm just going to put that into a calculator. By the way, that's the same.
Welcome to EDU Space.
So in this question we are given right?
That gives me 500. So now we need to know the angular frequency at which the tower
Now what we're going to do over here is that we are going to
is 1 half. I'm just going to put that into a calculator. 1 half.
circle, right? Over circle. Welcome to EDU is going to be head over here, right? And we will take help of the example 10.6, right? So we can start working on the problem. Now to be able to build a circle, we need the answers, right? So we are working on the equation 10.13, right? So after that, I'm going to ask the problem
The current
right, and that is equal to sum of the
V0
plug in the values and we get that it right, now we also need the radius of the circle, right, and that can be found out by dividing the expression that is underneath.
And when I write V0, I mean delta max. Delta
plus
max Z.
Right, so again we have all the values, we just need to plug them in. Get that equal to 3.46 into 10 raised to 1
The inverse tangent.
right, and that is approximately equal to 346 right, now all we need to do is that we need to draw circle,
Draw a triangle division like this. Phi is here. Minus is here. R is here. E is there.
set of screens
So the
are
cosine would be adjacent over hypotenuse, r over v.
So let's first of all equalize our right?
1 half should be a square here.
So as you can see over here, right, that given the point of strain, right, they are open at right D. And this is the right? Right? Now, what we need to do over here, right,
and we want this to be 1 half maximum value. Maximum value is 500. This needs to be 250. And we need to determine the angular frequency. So let me just keep right over here. I'm going to take this, multiply it by 2. So it's going to show us delta V max
Now we need to find out the other
over D squared.
So 600
D squared is going to mean r squared plus L minus C.
Right, now what we need to do is find out the maximum.
So now I'm going to put that in a calculator.
Right, so for that we have the next gamma plus maximum
minus there.
So we can simply just replace the
Okay, so I'm going to put that in, and then I'm going to look for the x-intercepts. So we max 100. And r was 10. 10 squared minus plus omega everything. Omega. So L is 2.
Right, now since the principal strains they have the same signs, right, then the actual vector strain would be
to the negative fifth power. And then I have to put in squared. Not squared. Minus 500 squared. Great.
Welcome to EDU World Space.
So in this example, we have an inner shell of positive 2q charge and an outer shell of minus 4q charge, and we're going to find the electric field everywhere. So, to begin, we need to write down Gauss's law. Closed line integral, closed loop integral of E dot dA equals the total charge inside divided by the Also remember that when we have a point charge, we can say that the electric field equals kq, the total charge inside, divided by r squared, distance away. K is just a constant, 9 times 10 to the 9. You can also write it in terms of epsilon, and this equals 1 divided by 4 pi epsilon naught.
221.
Okay, so let's find the electric field. Alright, so right at this green spot, we are on the inside of this inner shell. There is no charge here. If there is no charge, then it is 0, so the electric field must also be equal to 0. Inner shell of positive 2q charge. What about in between our first shell? So A and B to write down Gauss's law. Remember that in a conductor, the total electric field must be 0. So, there's no charge on the inside, nothing's induced, E must also be 0 there. B less than R less than C, from this first ordered region. Our inner shell has a total charge of plus 2Q, and so that is what would be Q enclosed here. So Q enclosed is plus 2Q. So that means that the electric field can be written as a charge in terms of epsilon, just as writing it like that, we get 1 divided by 4 epsilon 0 times the total charge inside, which is 2Q, divided by R squared, put about in between our first and let's see now, C less than R less than D, so now we're in this outer region, okay? So, if we're in this outer region, I know that electric field must be equal to 0 here in this region, because when you're in a conductor, the electric field must be 0, that's plus 2Q here, so I need minus 2Q on this inner surface. But in general, still 0 there, because we're inside the conductor. And finally, when we are outside this system, all we have to do is take the total charge, which is 4Q plus 2Q is minus 2Q inside, so Q enclosed is minus 2Q divided by, and we get E equals 1 divided by epsilon times minus 2Q. See now? So, from this other region, right?
10 squared.
We can go ahead and graph this. And what do we see? 0, 0. So, 0 here. 0 there. So, I need between B and C. We see 2.
Omega C.
4 products of 0 are squared. And now, we have to remember one of the properties. So, even though that this is a quadratic function, when you get out your graph institute here, and see what happens when you have a negative value outside of
So I want to look at this from
your
a different
expression.
perspective. This was for
So I'm breaking it now.
power dissipation in the whole circuit.
To see what happens when you have a negative sign outside of the expression.
This down here is just for the resistance. So if I know the current I sub 0, which is just
It looks like
average W max
something like this. Now,
then I can square it. I squared R.
more, when we graph it, there will be 2 solutions. We couldn't choose the physical solution. And so, in this instance, it will be something like
And then
so.
phi is R sub 0. And so that's going to give me 1 here.
Alright, there we go. Okay, so now we can look at the charges that are around these shells.
R squared.
Okay, let's look at the inner surface of our small. The inner surface of our small. Remember, electric field must be 0 if there's nothing
And again,
inside of this guy where that green dot is. So, this guy must be 0. What about on the outer surface? Outer surface must be the total charge on the shell. It's 2Q.
I didn't want it to be 500, I wanted it to be 250.
Okay, let's look at the large
This
one.
one was wrong.
Okay, on the inner surface, we need to have an electric field of 0, so it has to cancel the total charge on this inner shell. So we need a negative 2Q on that inner surface. Alright, okay. And then what about on the outer surface?
Okay, so I did make a mistake there.
On the outer surface,
Let's go ahead and fix what's above then.
let's look over the outer surface. The inner surface is, think about, okay, well there's minus 2Q right here. Inside of this guy, what has to be out there?
That's right, so it should be 2 and 2 there.
minus 2q.
And then down here,
That's the only way for me to
multiply by
net
2 on both sides to give me
charge
500. So I'm going to do delta V max squared r squared over the
inner surface
third half of the
total charge I use. So we need a negative 2.
okay, minus 2q. Let's put that in.
And then
And then down here,
Welcome to EDU World Space.
delta V max 100 squared.
okay, so we
R
have
squared
2 concentric shells, and a radius A, and a radius B of the inner shell, and a radius C, and a radius D of the outer shell. The inner shell has a total charge of plus 2q, the outer shell has a total charge of minus 2q, and we're going to find the electric field everywhere, and let's get started. So remember that when you have a point charge, the electric field is given by this. Remember what K is? K equals 9 times 10 to the 9. It's also equal to 1 over 4 pi epsilon. Epsilon is just a constant. Also remember Gauss law. Here it is.
Okay, let's see what that gives.
It says that the closed loop integral of E dot dA equals Q, the total charge of closed divided by epsilon. Alright, so, first region, radius less than A. Okay? We are right here in this little green dot. We have no charge there. With no charge, Q is 0, so E must be 0. So, remember, okay, A less than R less than B. We're in this inner shell, first, our smaller shell. This is a conductor. One of the properties is that E is 0 is essential to 9. So it's also equal. B less than R less than C. So now in this first region. Well, what is the total charge in that region? Q enclosed. Also, remember, it's just the charge of that inner shell plus 2Q. So, now we can just imagine that it's a point charge and say that the electric field A equals 1 divided by. Alright, so first 4 pi epsilon times Q, total charge inside, 2Q over 4 squared. Alright, now we're in our outer shell. C less than R less than D. We're in the C less than R less than D. Well, do our Gaussian surface for similar inductor. What is the total charge in here? Well, it must be 0. Why is that? We're inside of a conductor. So, E equals 0. There it is. Bad. Now what happens if we are outside of it? So now what happens if we are given a Gaussian surface outside of this? Well, what is the total charge enclosed? 1 plus 2q minus 2q, that equals 0. E plus 2 equals 0 times q. We can go ahead and graph this. 2q, 0, 0. So we have these features of 0. B to C, just something like this, it's 1 squared. C goes straight back to 0.
40 ohm resistor.
Alright, now let's look at where these charges might be located. So, what is the charge on the inner surface of our smaller sphere, or smaller shell? So, if we are looking at this region right here, well, I know that the electric field must equal to 0 here. There's no charge on the inside here, so we can reduce to what about the outer? Go right here. Well, what is our charge enclosed here? Plus 2q. It's everything. Everything is in there. 0. Electric field due to a plus 2q charge. B to C.
What frequency?
Just it's 2q.
250 watts.
What about our large shell? We go right on this inner diameter right here where these charges might be located. Okay, we know that the electric field must equal 0 here. That means it needs to cancel with this plus 2q that's happening right here. That means all of the minus 2q is going to land at this surface. Minus 2q.
No, this is 120 volt. Delta.
And what about this outer surface?
Max. Oops, that's delta
It's got to be 0. So we have a net charge of 0 here.
RMS is 120 volts.
So
we're
the outer
using RMS here.
must equal 0.
Goes to be RMS. I'm going to get rid of the 1/2 factor. RMS. Okay. Now we want this to be 250 watts.
That means all of the minus 2q is going to land.
Welcome to EDU World Space.
Well,
okay, so for this problem we have an inner shell and an outer shell. And the inner shell has a charge of plus 2q, the outer shell has a charge of plus 4q. The inner shell is bound by the radii A and B, the outer shell is bound by the radii C and D. So we can pull the electric field everywhere and see if we can find where the charges are going. So let's go ahead and look for the electric field everywhere. So, in order to find the electric field, we're going to write down Gauss's law, which says that the clothesline integral of u dot dA equals the total charge that is enclosed in our region divided by epsilon 0. So, in general, this is Gauss's law. And this is our this is our total charge enclosed in a Gaussian surface. This is epsilon 0, just a constant. And E is the RMS. So let's look for our first region, which is when we have a radius less than A. So for r less than A, well, we don't have any charge there, so that means that Q equals 0, Q equals 0, E equals 0. So, in order to find the electric field, we're going to write down Gauss's law, which says E equals 0. The integral is going to be A. Alright, what about if we are in between A and B, so we're in the shell right here? Well, if it is a conducting shell, then by definition, it must have 0 electric field. So we have the same thing. E is equal to 0 here. So let's look. Now what about this cavity between B and C? So for A, B, charge less than R, C, 0. Well, now we do have some charges. We have the total charge on this shell. That's 2q. So, just in general, we know there's a formula for the electric field of point charge. Right, equals K, which is 1 over 4 epsilon, or 99. KQ, by definition, divided by R squared, 0. We can use this for our region between C, and we see that the electric field E equals K. Now what about this Q, which is 2 R squared? Q right here is the total charge divided by R squared. R squared is just well, now we do have some charges. The total charge, we can write this more explicitly. 1 divided by 4 pi epsilon. Just in general, we know there's a formula for the electric field times 2q over R squared, which is 1 over 4 epsilon. Now what about the region C and D? So now we are in this outer ring. Well, when we are in this outer ring, Remember that the electric field must equal 0 because it is a conductor. So, for the region between C, less than R, less than D, E equals 0. He right here inside that conductor. Okay, and then finally, what about if we are outside of this object? So what happens if R is greater than D? Well, when R is greater than D, then we have the total charge enclosed, which is 4Q plus 2Q, 6Q. So we just can use this formula right here for our regular point charge, and we get our electric field E, well, equals 1 divided by 4 pi. So, epsilon 0 times 6Q over R squared.
And I get another frequency.
And then finally, what about if we are outside? Those are all the regions, now we can go and graph them. So if we wanted to graph it, it would look something like this. So we have R, and we have D, and we have 2QA, B. So we'll just see D
and 2,100 charge.
Okay,
the graph, by the way,
and we are going to get between region A and B. And what about between C and D? Epsilon 0 times 6Q. Originally, 0 charge. We just go inside of that inner shell. And between regions B and C, here's our so, because it's 1 over R squared,
actually is
something like this, and we see a similar function for when R is greater than D. However, this time, we are going to have a different prefactor in front, and it's going to be a little steeper, something like that. Okay? So, and so that denotes that. Now, what about the charges on the inner surfaces?
So start by drawing a diagram here.
Okay, so the inner surface, the inner surface is C shell. Well, because it has to be 0. Why is that? Because the electric field is 0 and we have a Gaussian surface right here, so this guy is 0. And see a similar function, you can have the charge right there, there's a thing inside. This time
is draw
inner
vector A, B, and C. So I'm seeing that A is 0 here. B is over here.
Okay, what about the outer?
And down here.
All the outer surface right here used to contain all the charge for this inner shell. So it must be plus 2Q. Okay, and what about for our large?
Alright, so let's get the components of UA,
Okay, so here's the inner. So we get a Gaussian surface right here. We know that we must have net 0 electric field.
And then in the negative y direction.
The only way for that to happen is that there must be an induced negative 2Q charge inside right here. So it has to be negative 2Q. Why is that? Because we need E net to equal 0. Okay?
Okay,
surface. Gaussian surface.
We've got an x
Let's just
component
total
and a y
charge,
component.
4 plus 2.
The x component is 2 cosine 4. So let's get that.
And that's that. Also, another thing to note about this graph is that this is, if we were to have units on this, we would expect that this would be a bit taller than this. Because this is 6 divided by 4 pi, and the difference is 2. So this is a way of checking. And that's that.
X component is negative 1.
Let's just total charge.
The y component is 0.
Welcome to EDU World Space.
The y component is
Also, another thing to note about this graph is that this is
my axis mixed up. The x component is 2.
Taller.
And the y component is negative 1. And there is no k. Alright. So, force AC is in the direction negative. The x component of A to C. So I need UAC, which is going to be UC minus UA. So 2 minus 0.75 is 1.95. The x component is 2 minus 1J. And then minus UAB is going to be B minus N. 240 minus 0.628. Different directions. B minus A. 2 cosine 40I. So I need 2 sine 40 minus AB. So minus 3.75 J minus 4J. So, we're told that, and I'm going to draw it on the diagram here, force AB 200 minus, and force AC minus 400 newtons. So if I take, let's go ahead and get AC first. The force, AC direction, is going to be, when force AC 400 times 1.25 over square root of 1.25 squared plus 1 squared and plus 3 squared. It's going to be in the I direction. Plus, same type of thing, J direction. Plus, same type of thing, K direction. Let's get these. Calculator. 400 times 1.25 over the square root. 1.25 squared plus 1 squared plus 3 squared. That gives me 147 squared. Now J is going to be -1 in the numerator right there. So I'm going to put -1 in the numerator. J minus 117.6. J. Then for K, all I have to do is put a -3 in there. 449 K. So AC, I'm saying, is in the negative J and negative K direction. And that makes sense. Yep. Okay, as we use that is going to be 250. Now J is going to be negative times 2 cosine 4K. Square root of 2 negative 40 squared. Now then for K, all I have to do is 2 sine 40 minus 0.75. Okay, as we use squared. 250. So AC, I'm saying negative 2 cosine 4 I plus same type of thing J plus same type of thing K. So this one 2 sine 40 minus 250 times 2 cosine 40 over square root parentheses 2 cosine 40 squared plus parentheses 40 sine 40 minus 0.75 squared plus 9. Okay, that gives me 112.3. For J, I just
Welcome
have
to
to put
EDU World
in
Space.
So in this example, we have an inner shell of positive 2q charge and an outer shell of minus 4q charge, and we're going to find the electric field everywhere. So, to begin, we need to write down Gauss's law. Clothesline integral with a closed loop integral of E dot dA equals the total charge inside divided by epsilon naught. Also remember that when we have a point charge, we can say that the electric field equals kq, total charge inside divided by r squared, distance away. K is just a constant, 9 times 10 to the 9. You can also write it in terms of epsilon, and it is equal to 1 divided by 4 pi epsilon naught. Okay, so let's find the electric field. Alright, so right at this green spot, we are on the inside of this inner shell. There is no charge here. If there is no charge, then Q is 0, so the electric field must also be equal to 0. Inner shell has a 2Q charge and minus 0Q charge. What about in between our first shell? So A and B. Remember that in a conductor, the total electric field must be 0. So, there's no charge on the inside, nothing's induced. B must also be 0. That way we have charge. We can say that B less than or less than C, we're in this first ordered region. Our inner shell has a total charge of plus 2q, and so that is what would be Q enclosed here. So Q enclosed is plus 2q. Okay, so that means that the electric field can be written as a point charge in terms of epsilon, so just as K. Writing it like that, we get 1 divided by 4 pi epsilon 0 times the total charge inside, which is 2q, divided by r squared. And let's see now. C less than R less than B, so now we're in this outer region, okay? So, if we're in this outer region, I know that electric field must be equal to 0 here in this region. Because when we're in a conductor, the electric field must be 0. That plus 2q here, so I need minus 2q on this inner surface. But in general, it means that they still must be equal to 0 there, because we are inside the conductor. And finally, when we are outside the system, all we have to do is take the total charge minus 4q plus 2q is minus 2q inside, so q encloses minus 2q divided by, and we get E equals 1 divided by epsilon times minus 2q over r squared. Okay. So, in this outer region, I know that, right? We can go ahead and graph this. And what do we see? 0, 0. So we need 0 here, 0 there, so we need between B and C. We see, but in general, 2 still over 4 pi epsilon 0 r squared. And finally, we are out. And now, you have to remember one of the properties, so even though that this is a quadratic function, you can get out your graphing calculator and see what happens when you have a negative value outside of your expression that you're working with. So I'm graphing it now, and I think that all of you should graph it as well. To see what happens when you have a negative sign outside the expression. You can see it looks like
Let's verify that that's correct.
And now, even though that this is a more, excuse me, when you graph it, there will be 2 solutions. Make sure that you choose the physical solution. And so, in this instance, it will be something outside your expression. Alright, here we go. Okay, so now we can look at the charges that are around these shells. Okay, let's look at the inner surface of their small. The inner surface of our small. Remember, electric field must be 0. There's nothing on the perimeter inside of this guy where that green dot is. So, this guy must be 0. What about on the outer surface? Outer surface must be the total charge on the shell. Okay, let's look at the large one. Okay, on the inner surface, you need to have an electric field of 0, so it has to cancel the total charge from this inner shell. So we need a negative 2q on that inner surface. Alright, okay. Okay, then what about on the outer surface? Well, on the outer surface, okay, all we have to do, the inner surface of our small is, think about, okay, well there's minus 2q right here, inside of this guy, what has to be out there? Minus 2q, but on the outer surface. Outer surface. That's the only way for the net charge to be like this. So the inner to be okay. Minus 2. Okay, on the inner surface, you need to have this so it has to cancel the total charge in this inner shell. So we need a negative 2q on that inner surface.
Welcome to EDU World Space.
Drawing from the previous problem.
Okay, so we have two concentric shells, and a radius A, a radius B of our inner shell, and a radius C, and a radius D of the outer shell. The inner shell has a total charge of plus 2q, the outer shell has a total charge of minus 2q, and we're going to find the electric field everywhere, and we're going to so let's get started.
Well,
so remember that when you have a point charge, the electric field is given by this. Remember what K is? K equals 9 times 10 to the 9. It's also equal to 1 over 4 pi epsilon. Epsilon is just a constant. Also remember Gauss' law. Here it is. Gauss. It says that the closed loop integral of E dot dA equals Q, the total charge of closed, divided by epsilon. Alright, so, first region, radius less than A. Okay? We are right here in this little green dot. We have no charge there. With no charge, Q is 0, so E must be 0. So, okay, A less than R less than B. We're in this inner shell, first our smaller shell. This is a conductor. One of the properties is that E equals 0 instead of 9. So it's also E 0. B less than R less than C. So now we're in this first order region. Well, what is the total charge in that region? Closed and closed. Also remember, it's just the charge of that inner shell. It's 2q. So now we can just imagine that it's a point charge and say that the electric field AE equals 1 divided by, alright, so 4 pi epsilon times Q, total charge inside, 2Q over R squared, there it is. So E alright, now we're in our outer shell. C less than R less than D. C less than R less than D. Well, do our Gaussian surface, some conductor here. What is the total charge in here? Well, it must be 0. Why is that? We're inside of a conductor. So, E equals 0. There it is. Sounds not too bad. Now what happens if we are outside of everything? So now what happens if we are given the Gaussian surface outside of this system? Well, what is the total charge enclosed? 1 plus 2q minus 2q, that equals 0. E is equal to 0 here as well. We can go ahead and graph this. 0, 0, so we have these regions of 0. B to C, right? Now we're in the outer shell. Something like this, it's 1 over squared.
Okay,
So I think straight back to 0. Alright, now let's look at where these charges might be located. So, what is the charge on the inner surface of our smaller shell? Our smaller shell. So if we are looking at this region right here, well, I know that the electric field must equal 0 here. There's no charge on the inside. Force induced must equal 0.
So we do have enough.
What about the outer? So right here. Well, what is our charge enclosed here? Plus 2q. So we go ahead and grab this. Everything is in 0. 0 electric field due to a plus 2q charge. B to C. Fourth plus 2q.
If I plug all of those in here, it's just
on our large shell. We go right on this inner diameter. Right here where these charges must be located. So what is the okay? You know that the electric field must equal 0 here. That means it needs to cancel. So with this plus 2q that's happening right here. That means all of the minus 2q is going to land at this surface. Minus 2q. Then what about this outer surface? Well, it's got to be 0. We have a net charge of 0 here.
We know F sub x. Oh, we know F sub x.
outer must equal 0 plus 2q. Is on our large shell.
Alright, so we don't need these two. All of these together are 10. There's really only 4 on each cosmos.
Welcome to EDU World Space.
So let's go ahead.
Okay, so this problem we have an inner shell and an outer shell. And the inner shell has a charge of plus 2q, the outer shell has a charge of plus 4q. The inner shell is bound by the radii A and B, the outer shell is bound by the radii C and D. We can put the electric field everywhere and see if we can find where the charges are going. So let's go ahead and look for the electric field everywhere.
1.25.
So, in order to find the electric field, we're going to write down Gauss's law,
That equation
which says that the closed line integral of B dot dA equals the total charge that is enclosed in our region divided by epsilon 0. So in general, this is our Gauss's law, and this is our area element. This is our total charge enclosed in our Gaussian surface. That's epsilon 0, just a curve. And E is what will be in our shell. So let's look for our first region, which is when we have a radius less than A. So for r less than A, well, we don't have any charge there, so that means that Q equals 0, Q equals 0, E equals 0. So, in order to find the electric field, we're going to write down Gauss's law, which says E equals 0. We have the closed line integral, so we can take dA. Alright, what about if we are in between A and B, so we're in this shell right here? Well, if it is a conducting shell, then, by definition, it must have 0 electric field. So we have the same thing. E must equal 0 here. So let's look for which is
5 squared.
Now what about this cavity between B and C? So for A will be charge less than R means that C is 0. Well, now we do have some charges. We have the total charge on this shell plus 2q. So just in general, we know that the formula for the electric field of point charge, E, right, equals K, which is 1 over 4 pi epsilon, or 99, KQ, then, by definition,
That is correct.
divided by R squared, 0. We can use this for our regions between B and C. And we see that the electric field E equals K. Now what about Q, which is 2 here? So Q right here is the total charge divided by R squared. R squared is just, well, now we do have some charges. The total charge, we can write this more explicitly. And divided by 4 pi epsilon, just in general, we know that the formula for the electric field times 2q over R squared, which is 1 over 4 pi epsilon. Now what about the region C and D? So now we are in this outer ring. Well, when we are in this outer ring, remember that the electric field must equal 0 because it is a conductor. So, for the region between C less than R less than D, E equals 0. E right here inside that conductor. Okay, and then finally, what about if we are outside of this object? So what happens if R is greater than D?
Essentially, staggering 0. here.
Well, when r is greater than d, then we have the total charge enclosed, which is 4q plus 2q, 6q.
Total length.
So we'll just use this formula right here for our regular point charge, and we get our electric field E
I'm just going to solve for z.
1 divided by 4pi.
So
So
it's going to be the square root
0 times 6q
of 8 squared
over r squared equals 0.
minus 4 squared, which is 13, minus 2 squared, which is 4.
Finally,
So it's going to be 16.
those are all the origins. Now we can go ahead and graph this. So if we wanted to graph it in a meter like this, so we have r,
The answer
and we have d,
done. Easiest question
and
in
we
this
have
unit so far.
q, b. So we'll just use the formula right here, d, charge, and we get k, and we are going to get between regions A and B, 1 divided by 4. And what about between C and D? 0.
Okay. Question one. We are looking for
Originally, 0 is the charge inside the inner shell. And between regions B and C,
from the game's mass.
so because of the 1 over r squared, so something like this, and we see a similar function for when r is equal to d. However, this time we are going to have a different row factor in front, and it's going to be a
Final velocity
like that.
negative 1.2.
And so that's that.
In this case, it's
Now,
negative.
what about the charge
moving
moving
backwards away from the surface? Facing the wall, moving backwards. We have a negative velocity. This is all done. Time interval delta t.
Okay, so the inner surface, the inner surface that's the inner shell. Well,
In the end, it's
it has to be the electric field is 0 on when we have a Gaussian surface right here. So this guy is 0. We see a similar surface right over here. There's also the inside. This time, so inner inner is 0. And I guess we put this okay, what about the outer?
Minus momentum initial.
All the outer surface right here.
Now in this case, we already said
We see contain all the charge
starting at rest is
for this inner shell. So it's 3 plus 2q.
0. Momentum.
Okay. And what about for our large?
Momentum is equal to mass overall velocity. Here, this will be our mass times our final velocity. Write that in.
Okay.
Mass
With the inner.
final. Now in this case, we already said equals our final
So
momentum.
we do Gaussian surface
Divide the
right
change
here.
in time.
We know that we must have net 0 electric field.
So we've solved
The only way for that to happen is that there must be a reduced negative 2q charge on the inside from here. So that's a negative 2q. Why is that? Because we need E net to equal 0. Okay.
per second. The negative is
The
important.
outer surface,
That y, when we get to us at the answer here at the end,
Gaussian surface.
our delta t is 0.
That's just the total charge, 4 plus 2.
Here, back in the square math. So we solve 0. Find that in the end, our force is equal to
And
negative
that's that.
69.
Also, another thing to note about this graph
There's a negative sign is
is
significant here.
that this is, if we were to have the units on this, we would expect that this would be 15 taller than this. Because this is 6 divided by 4 by 2. Anyways, check. And that's that.
Right. Question number 10. We have a stream of water strikes a stationary turbine blade horizontally. Picture of the text. And then what we are asked to find the magnitude of the average force exerted on the water by the blade. One key piece of learning from this problem.
Welcome to EDU World Space.
What it tells us the mass of water per second is like 30 kilograms.
This is
We are going to assume, for our problem's sake, that this is all happening in a 1 second interval. Question number 10. Okay, let's get started. So we are given in this problem that the water, and then initial velocity, beyond 16 meters per second. And when it strikes this blade, that final velocity, we have negative 16 meters per second, moving exactly in the opposite direction when that's done. And like I mentioned, we're going to talk about this happening in a time interval of 1 second. That allows us to identify the mass of the water that's moving in that 1 second to be 30 kilograms. 16 meters per second. The reason that we want to do this is because we now can use impulse momentum theory to solve negative impulse momentum theorem is F delta T. And like I mentioned, we're going to initial change in momentum and that force is what we are breaking. This blade is allowing us to identify the mass of the water that's moving. So we have force times delta T equals delta P by delta T over. Like I mentioned, we're going to force E final minus T initial, delta P, divided by delta T, mass of the water that's moving in that change in mass is going to be 30 kilograms because we define this as a 1 second interval. Remember that momentum equals mass times velocity. So our momentum final would be mass times velocity final. Our momentum initial, mass times velocity initial, divided by delta T. Because mass is the same code, we factor that out. Gives us force equal to mass times delta T. The final minus the initial by delta T all over the time intervals delta T. To solve this correctly, remember that now we're ready to substitute numbers. Mass was 30 kilograms, travels by 1 second. The V final is negative 16 meters per second. 30 kilograms, so we define this as minus the initial velocity, which is a positive 16 meters per second. Momentum equals mass final velocity minus initial momentum final with power times all of 1 second. And we get an average velocity of 960. Final negative 16 initial all over initial velocity solve the second. Final number 9. We have a rocket that is a space probe. Sorry, not initial velocity. Space probe has a rocket attached to it and is traveling in outer space. This retro rocket is fired to slow down the probe, and we are being asked to find the momentum of the probe after the retro rocket ceases to fire. Okay. So let's start again with what we know. We know that initially, the space probe has 7.5 times space probe to be 7. meters per second of momentum initially. We know that the retro rocket applies an average force to space probe 10/60 force. Now, this is where the little trick is. You have to read between the lines a little bit the fact that it is a retro rocket, which means it's going to be firing in the opposite direction of the motion. So the motion, which is defined here as positive because of the initial momentum of the rocket. So if the motion going forward is positive, anything working against it will be negative, which means that this force that the retro rocket is applying is a negative force. And then we know it applies this negative force now in a time interval of 12 seconds. We are asked what is the final momentum of the space probe when it's all said and done. So let's look at our impulse momentum theorem. Force applied, motion going forward, time interval that it happens during. This is where it's equal to change momentum. Retro rocket applies a retro rocket force, T, opposite direction final, minus momentum initial. In this case, we are looking for momentum final. So we're going to add over momentum initial to the space probe. T, let's look at plus the initial equals our final momentum during. Now we can plug numbers in. So negative 2.0 times 10 to the 6th newtons. Force exerted by the retro rocket. Done. 12 second interval. Add that to the initial momentum that the space probe had. 7.5 7th kilogram final meter per second initial. And that equals 2.0 and over 6 newtons. Force exerted by the retro rocket per second. Now again, in this problem, it was more.
Welcome to EDU World Space.
Understanding where the negative sign is. Negative sign is retro booster in the rocket. Just make sure you catch that one. That's all. Force exerted by the retro rocket.
Well, now usually found that it is not equal. If I'm not equal, we have the maximum and the zero and the random down system. Simple transforms into the situation. Again, in this problem, 6
Welcome to EDU World Space.
Draw a circle. This point is going to be the one, this point is going to be the two, this point is let's not compare this thing. So for the x1 lines is just to accelerate because the radius which is equal to 870 for x12 is just 105 and the maximum improvement this way is just 2 centimeters, so this is 165. have to draw another circle which touch the origin and the epsilon 2. And then draw the big circle that over those two circles. This one, the y-axis this one will be the absolute maximum shear strain 2. So it's just that absolute maximum shear strain is equal to epsilon 1, which is 670.
Welcome to EDU World Space.
To find the equivalent frame at the orientation of 30 degrees counterclockwise from the original plane. So first we have to draw the null circle, and to draw the null circle we have to determine the center and radius of the circle, which I have already done that. And then, the next step is we have to determine the original plane of the circle, which can be found by
Welcome to EDU World Space.
X and from X by 2, which is at this point. It's 150 and it's and we call this point A, and that's our original plane. And for the new plane, which will be 30 degrees clockwise from the original plane. In more circles, it will be 60 degrees clockwise from the original plane. Looking at this point B. This is epsilon x dot, and this will be the new shear strain. And for epsilon 1, it will be at this point. And that's the point of our Note that this angle is 60 degrees defined and 60 degrees, and so that means this angle is 34.09 degrees. So this one is just X1 X back is just which is the radius cause that angle 34.09 and plus the center. Not that easy, but 6 X dot, and for the tau is the radius from the angle and it will be minus 6. The minus because this is the upper side of the circle. Now,
Welcome to
all
E space.
some like that, and is the center minus the radius equals 4.49, which is means 116 minus 6, and these are the answers.
Welcome to EDU World Space.
So in this question we have been given the state of strain that we are studying, right? So in this the strain acting on the x direction is equal to 300 into 10 raised to power negative 6. Acting on the y direction is equal to 550 into 10 raised to power negative 6, right? And the shear strain is equal to negative 650 into 10 raised to power negative 6, right? And the strain that is acting in the z direction is 0 because there is no strain that is acting in the z direction, right? Now we are going to use the Mohr's circle theory, right? And for that we are going to build the circle, and so for that we need the exertion we have, and we're going to use the equation 10.1 gives us that, right? So we have OC that is equal to the average value of the strains, right? So that is the sum of the strains divided by 2. Right, and you calculate it together is equal to 425 into 10 raised to power negative 6. Right, now all we need to do is that we need to find out the radius of the circle, and we have the expression for the circle for radius as well, right? So we have underneath the difference of the circle strains divided by 2 whole square plus the shear strain divided by 2 whole square. You have the values, you just need to plug them in, and you get that's equal to 3.2, 3.8 to 1, right? So we have 1 into 10 raised to power negative 4, right? And that is approximately equal to 348.2 into 10 raised to power negative 6. Right, now what we need to do is that we need to draw the circle. Right now, alright, so let's take a look at that. Find out the radius of the circle, and we have the expression for the circle for radius as well, right? So we have underneath. So now as you can see over here that this is the point A at which the rate of strain is occurring, right? So we need to measure the angle from this point, right? So now the principal strains are easy to find, right? Because we'll take the help of the circle. Now for that, principal strain is equal to OC negative R, right? So you have the values, you just need to plug them in, and you get that equal to 67.8 into 10 raised to power negative 6, right? And the other principal strain is circle OC plus R, right? Again, you have the values, just plug them in, and you will have your value. You answer in no time, right? So we have 770. So now as you can see over here, into 10 raised to power negative 6. Right? So now that we have the value of the principal strain, we need to find out the maximum right? In plane shear strain, right? That is given by this divided by 2 and equal to r, right? So when we shift this 2 over here, so we can easily find out the value of the maximum influence shear strength, right? So gamma sub maximum in right plane, that is equal to r, that is equal to the difference of the principal strains, right? So you have values, you just need to plug them in, and you have your value, that is 696 into 10 raised to power 6. Right, now since the principal strains, they have the same sign, right? They have the same sign, so same sign means that we can directly have the expression for the maximum value of the strain, a shear strain, right? That is maximum, right? So the principal strains is equal to 773 and 10 raised to
Of course, I'll begin by drawing the diagram.
This includes our solution, right? So gamma sub maximum in right plane,
X, Z, there are 3 forces. F2.
Welcome to EDU World Space.
F3.
So let's solve this question. So in this question we have epsilon A equals to epsilon X equals to here plus epsilon Y into
And
minus here
F1 that appears to be in the
plus gamma XY into cos theta
It's convenient.
sin theta. Following this, epsilon X equals to epsilon Y equals to 0. Substituting the value, we get gamma XY equals to be 5.7 minus 4 UA Y1 bar A1 minus Y2 bar
Since
A2.
F1 is
we get UA as 0.0653. Now we have tau XY
Right angle symbols aren't in there,
Welcome to
but
EDU World Space.
I think that's what they are showing us.
tau X
Writers.
tau pi by
So,
plus epsilon Y
F
d4 minus d4 is
proportion
minus d. So that means tau xy minus plus is equal to e. Now we have tau xy plus
of course I could do this in my head.
gamma xy. So this is what 98.997 to p plus to 5.6 2 times power 6 5.76 that is minus
Is going to
p comes out to be 0.05.
Z, that's what they are showing us. The 3 fifths of 90. So, of course I could do this in my head. 54. Proportion, they are both in the
Welcome to
positive
EDU
direction.
World Space.
F2.
So in this question, the radius
F
is
in negative
right? The material that is over here is D. The tension that is provided over here is of magnitude
So now let's get
right? And we are required to determine the strain along the x dash direction and the y dash direction, right? Now, the thing to note over here is that as there is no load that is
we are given
applied over here, right? So it means that if there is no load, so there would be only torsion present. And as there is only torsion present, so it means that there would be no stresses. It means the stress in the x direction is equal to the stress in the y direction, that is equal
Welcome to
to
EDU
0,
World
right?
Space.
And if there is no stress, so it means that there is no normal strain, right? So
I
it
like
means
to
that
write
the strain in the x direction is equal to the strain in the y direction, that is equal to 0, right?
I like to
So
write
now since this is on here up, let's write the strain elusive equation for 45 now, if we, right? the strain result equation for 45 degrees is that is the strain applied along the x dash direction is
Again, I can think
the x direction also plus y
cosine of 60.
along the y direction
I like to
zero, right? Strain along the x, strain along the y direction as 45 plus gamma sub xy sine 45 degrees and
F1
x
in the x direction.
right? Now we just discussed that the strains along the x and y direction are equal to 0, so it means that these two terms would become 0, right? So we get the system, so solve it and you'll get that
F2 in the x direction. F2 is going to be the 75.
positive gamma sub x, sorry, gamma sub x divided by x. Right, so let's look at this equation number 1. Now what we need to do is that we need to write the strain and get equation for 135 degrees. Now how do we get 135 degrees? So 45
Y direction is going to be the same thing, except there's going to be cosine.
right, so
Okay, they are both.
now what we need to do is that we write the result equation for 45 degrees. Now we just we have
5 sine
sorry, 135 135, 135 about 0, and all 135
Also
degree. Right? So again, these two terms would be and solve it and we get that it is equal to negative gamma by get 2, right? Let's not the equation. Now what we need to do over here is that we are going to use the torsion formula 5.6, right, which is torsion maximum is equal to T times V divided by J, right? And we solve that torsion is equal to G. Now what we're going to do is that we are going to compare these two equations and we will solve it for gamma, right? And when we solve it for gamma, we will get this expression, right? So what we're going to do over here is that we just plug in the values and we will get that gamma is equal to 0.050, right? So just plug it back in equation number 1 and we'll get that it is equal to
so I need to write this
positive
in Cartesian vector form.
divided by 2, that is equal to positive point is 0, 0, 2, 5, and this is equal to negative
72i.
5, 0, that is equal to 0.005, right, that is equal to that. Positive
Plus 54.
right? So this is the expression, right? So what we do is that we just plug in the values and we get gamma is equal to
F2 is 53.
Welcome to EDU World Space.
Plus
so in this question we are given the following state of expression and the point that we are starting, right? So the strain again is
and 3 is just 200.
Everything in the right direction right, and the shift is equal to 650 all the divided by 6, and
Welcome to the channel. Here we touch complex questions and break them down into simple step-by-step solutions.
and what we're going to do over here is that we are going to use the
Now, at least this diagram seems easier to see. A little bit harder to interpret. Let me go ahead and draw just what I can draw here.
10.6, right? So we can start working on the problem. Now to be able to
vertical, not y-axis.
Then right after that,
Okay, so continue this through. We've got a point B down here, which looks like the easy one. Definitely the easy one. There's a point A up here. So this diagram
right now we also
we're shown that this is 3.
right, and they are tending on our side.
This is 4.
Under
This is 2. So,
difference of the
since it's just that one, we've got a
plus
oh no, this is 1.5.
right, so we need to have all the values from that region to get that equal to 3.
And then point C back here. So, part of this visual, we've got a point down here, which is 4.
Right now, all we
But
need to do is
the hypotenuse is 2 feet, and the angle is 20. So I'm going to green this, and I'm going to indicate that this is 2 cosine 20. And this is 2 sine 20. The hypotenuse is 2 feet. Alright, so the distance from A to B
and this is the reason
for you, I'm going to indicate that this is going to be, x direction is going 1.5. In the y direction, it's going negative. I'm going 2 to 3, so it's only negative 1 foot. This is, alright, so the distance from A to U in the z direction is going down 4 feet.
And that is
This is AC.
now we need to find out the other principal square, so that is equal
So the distance from AC in the x direction is going backwards, so it's negative 2 sine 20. X direction is going 1.5. The z direction is going down in the y direction. Over 2 plus 2 cosine 20. That would be positive direction. In the z direction is going down.
So that we have going back gamma of maximum
2 sine 20. And then in the z direction is just negative.
that only divided by 2 and equal to r, right? So we're going to just get this here. We have
we need to figure out the resultant force. So, force AB is going to be FAB direction over U vector AB over U AB. So F is going to be, let's put this into a calculator, FAB, which I did not write down yet, but the book tells us that
right now, since the
FAB
same sign, right, then
20 pounds.
Would be
vector times U vector AB. I'm going to use the x component, negative 2. Nope. So, AB is going to be 1.5. FAB over the square root. 1.5 squared plus 1 squared plus 4 squared. Now, it's going to be...
Welcome to EDU World Space.
That gives me...
So in this example, we have an inner shell with a positive 2 charge and an outer shell with minus 4 charge. And we're going to find the electric field.
20 pounds.
So, to begin, we need to write down Gauss's law. Clothesline integral equals loop integral of E dot dA equals the total charge inside divided by epsilon. Also, remember that when we use the charge, we can say that the electric field equals K cubed, the total charge inside divided by r squared, the distance away. K is just a constant in our tank You can also write it in terms of epsilon, divided by 4 pi epsilon. Okay, so let's find the electric field. Alright, so right at this green spot,
now the denominator
there is no charge. If there is no charge, then Q is 0, so the
FAC, according to the book,
to
40 pounds. So it's 40 times.
What about in between our first and shell? Remember that in a conductor, the total electric field must be 0. So,
negative 2 squared.
B less than or less than C, unless first for the region. Our inner shell has a total charge of plus 2Q. And so that is what would be Q enclosed here. So Q enclosed, okay, C plus 2Q. So that means that the electric field can be written as electrons in terms of epsilon.
The numerator is negative
writing it like
2
that, we get 1 divided by 4 pi
negative 4.7
times the total charge inside, which is 2Q.
I'm going to put the 2 plus 2
divided by
20 in the numerator.
And let's see now. C less than R less than G, so now we're going to find the region. Okay. So if we're in this outer region, finding that the electric field must be equal to 0 here in this inner shell. Because when we're in a conductor, the electric field must be 0. And so that is 2Q here.
Add those
So
together
we
to get the
minus
result.
2Q on this inner surface. But in general, electric field can be
6.84 minus
because it was 4.7. And finally, when we are outside of the system, all we have to do is take the total charge, Q 27.6 divided by minus 2Q, and we get E equals 1 divided by epsilon, and times minus 2Q over R squared. So,
2 plus
right? We can go ahead and graph this, because again, what do we see? 0, 0, 0 here, 0 there,
and we're still not done.
B and C, but you can see 2. And finally, we are outside. And now, we have to remember one of the properties. So, even though that this is a quadratic function, you can get out of the graphing calculator and see what happens when you have the negative value outside of your expression that you're working with. So, I think that all of you should practice to see what happens when you have a negative sign outside of the expression. And see.
Nope, down.
It looks like something like this.
Check if that's the correct answer. Yes, it is. And then to get alpha, beta, and gamma, we just
when you graph
look
there
at
will
the
be
sign.
two solutions. Make sure to choose the physical solution.
FR,
And
which
so
is
in this instance,
0.97,
it would be
over
something.
FR, which is 52.1. Putting that in the plan.
Alright, there we go. Okay, so now we can look at the charges that are around these shells. Okay, let's look at the inner surface of our small. The inner surface of our small. Remember, electric field must be zero. There's nothing very inside of this guy. So, this guy must be zero. What about on the outer surface? Outer surface.
Gamma G to the numerator to negative 46.7.
Okay, let's look at a large one. Okay, on the inner surface, we need to have an electric field of zero, so it has to cancel the total charge for the inner shell.
And those are correct.
So we need a negative 2Q on that inner surface. Okay, so now we can look at, and then what about on the outer surface? Okay, on the outer surface, let's look at the inner surface. All we have the inner surface of our small is, think about, okay, well there's minus 2Q right here.
So you really do need the 3
as the last out there.
which says that x equals y.
Minus 2Q.
And so, this is a very good problem.
It's the only way to get the next charge to be like
This is an 8 millimeter long, 8 meter long
the inner surface, we need to have
if E is 5, and those are correct.
negative 2Q.
Then what are x and y? Understanding that x and y are really then need the 3.
Okay,
So,
and then
8 squared minus 5 squared.
Welcome to EDU World Space.
That's just
okay,
going to
so
be
we
64 minus
have
25.
two concentric shells here. Your radius A, our radius B of our inner shell, and radius C, our radius D of our outer shell. The inner shell has a total charge of plus 2Q. The outer shell has a total charge of minus 2Q. We're going to find the electric field everywhere, and where the charges are.
18.5.
Let's get started. So remember that when you have a point charge, the electric field is given by this. Remember what K is? K equals 9 times 10 to the 9. It's also equal to 1 over 4 pi epsilon. Epsilon is just a constant.
Welcome to EDU World Space.
Also remember Gauss' law. Here it is. Gauss says that the closed loop integral of E dot dA equals Q, the total charge of closed divided by epsilon. Alright, so first region, radius less than A. Okay, we are right here in this little green dot. We have no charge there. With no charge, Q is 0, so E must be 0. Okay, A less than R less than B. We're in this inner shell, first or smaller shell. This is a conductor. One of the properties is that E equals 0 inside of it's also equal. So
What are x and y?
B less than R less than C. So now we're in this first homogeneous region. Well, what is the total charge in that region? Also when we close, well, just the charge of that inner shell. So now we can just imagine that it's a point charge and say that the charge E equals 1 divided by radius plus 4 pi epsilon. Okay, times Q, total charge inside. We have no charge to Q over square root. So here it is.
19.5.
Alright, now we're in our outer shell. C less than R less than D. C less than R less than D. Well, do our Gaussian surface for some right here. What is the total charge in here? Well, it must be 0. Why is that? We're inside of the conductor. So, E equals 0. There it is. Well, it's not too bad. happens if we are outside of everything? So now what happens if we are doing a Gaussian surface outside of these systems? Well, what is the total charge of Hooks? Plus 2q minus 2q. That equals 0. Times E equals
So again, drawing the diagram and figuring out what it means is
0, 0.
most of the battle.
0. Alright, B to C. Right here. It goes something like this. It's
Y,
and then it goes straight back to 0.
X, and we need to continue to
Alright, now let's look at where these charges might be located. So, what
we're
is the
given
charge on the
F1,
outer surface of our smaller sphere? Or smaller shell?
up here,
So if we are looking at this
X
region right
again.
here,
That's going to be
well, we know that the electric field must equal 0 here. There's no charge on the
so
inside
it's a
here, so we're
3,
going to
4,
use
5 triangle, but it's got no text.
Go right here, plus 2q minus 2. Well, what is our charge very close here?
Okay. F1, we're given
0, 1. Electric field.
F2 has all 3 components. Y,
Plus 2q. But our large
but the
shell.
angles are
Right under the
directly
right here.
we're given F1.
Okay. We know that the electric field must equal 0 here. That means it needs to cancel with this plus 2q.
I guess it does.
All of the
And the angle with Y is 120. So yeah, they're all directly here.
minus 2q.
So let's go ahead and do F1.
Then what about this outer surface?
F1 in the X direction is
We
0.
have net charge is 0.
F1 in the Y direction is, well, it's going in the positive Y direction at 3/5
So the outer
of 450.
must equal
Well, 45 divided by 5 is 9. 9 times 3 is 27, so that's going to be 207 newtons in the positive direction. F1 is going to be 4/5 of 450, but it's in the negative direction, so that's going to give us negative 360 newtons. So let's move on to
Welcome to EDU
F2.
World Space.
This is actually all pretty
Okay, so
straightforward.
for this problem we have an inner shell and an outer shell. And the inner shell has a charge of plus 2q, the outer shell has a charge of plus 4q.
It's just going to be the
The inner shell is
525
bound by the radii cosine. The outer shell is bound by the radii CB.
X
We
direction.
can put the electric field everywhere and see if we can find where the charges are going.
Y
So let's go ahead and look for the electric field.
Cosine of the Y direction. What?
So, in order to find the electric field, we're going to write down Gauss's law,
And F2
which says that the Euler's line integral, or mu dA, equals the total charge that is enclosed in our region divided by epsilon 0. So in general, this is our Gaussian law,
So this Y one should
and this is our area element. This is just the positive enclosed in
So let's put them into a
calculator.
calculator.
So let's look for our first region, which is when the radius less than 3.
Cosine of 25.
So for less than A, well, we don't have any charge there, so that means that Q is
525 cosine
0,
120.
P is 0. So, in order to find the electric field, we're going to write down Gauss's law.
This negative 265 and 525 cosine of
Alright, what about if we are in between A and B, so now we're going to
is going to give us
well, if it is a conducting shell, then by definition,
okay, so now we have to add them together.
it must have
Adding the x
0.
components, well, there is only one x component. So that's going to be, so we're going to write it in vector form. 371.25.
Now what about this cavity between B and C?
So now I'm going to do 270 minus 262.5. I don't trust myself, so I'm
Well, now we do have some trouble.
270 minus 262.5.
That's too cute.
7.5. So,
just in general, we know that the formula for the electric field point charge
plus
is
7.5J.
K, which is
then in the K direction, we got negative
360. KQ,
plus 262.5.
that's squared. We can use this for our region between B and C, and we see the field
negative 97.5.
Now K, Q, which is 2. Q right here is this.
We need to sketch the vector, find the magnitude, and then so sketching the vector is what I would do next. We've got 371 in the I direction. Then we've got 7.5 in the J direction. And then we've got a negative J direction.
C and D.
So it's going to be like,
well, this outer ring. Remember that the field must equal 0 because it is a conductor. So, for the region between C,
now
D, to E equals 0.
we need to
Finally, what about if we are outside of this object? So what happens if we are
negative 97.5 squared?
well, when R is greater than D, we have calculator, which is 4Q plus 2Q, 6Q. So we just use this formula right here for our regular point charge, and we get field E equals 1 divided by 4 pi, so epsilon 0 C times 6Q D E over R squared.
2 over 384. Beta and gamma are very much the same.
So if we wanted to graph it, it would be something like this. And we have A, so B, C, D, and we get okay. And we are going to get between region 1 and B. Originally, 0 inside of that inner shell. And
7.5 in the numerator.
C. So it goes as 1 over R squared.
And negative 97.5.
And we see a similar function for when R is greater than D.
No,
This time, we are going to have a different point factor in front, and it's going to be so that's that. Now, what about the
Alright, now for the easier question, we need to figure out the coordinate direction angles for F1. So that's going to be, hey now, where that's red. Alpha 1.
0. Why is that?
Beta 1. And with the Z direction, gamma. So, alpha 1 will be the inverse cosine. Oh, wait a minute. I forgot to get the magnitude. F1. Oh, wait. We know the magnitude. It's 60. Silly. Alpha 1 is the inverse cosine. So that's going to be F1x, which is negative 19.3. Get the magnitude. Over 60. Beta. Oh, wait a minute. It's just 19.3. And gamma 1. We know the gamma 1.
We know that we must have net 0 electric field.
Negative 46.
The only way for that to happen is that there must be an induced negative to the cube charge on the inside of the
So just putting them into a calculator
turns out because we need net to 0. Okay? And on the outer surface,
3, 60,
that's just the total charge,
124, just 19.6. Positive 19.3.
Also, another thing to note about this graph is that
1.2.
this is, we're to have negative 46. We would expect that this would be
Negative 46.
taller than that. This is 6 divided by 1 equals 260.
Welcome to the channel where we tax complex questions and break them down into simple step-by-step solution by solving today's problems together.
Now, at least this diagram seems easier to see. It's a little bit harder to interpret, though.
Welcome to EDU
Let me go ahead and draw, at least what I can draw here. The poor job of drawing that y-axis. Let's try it again. At least this diagram. Okay. So, continue this through. We've got a point B down here, which looks like the easy one. Definitely the easy one. There's a point A up here. At least this diagram seems easier. And we're shown that this is 3. This is 4. This is 2. So, that's it for that one. We've got a point B down. Oh no. This is 1.5. These are all feet. And then there's a point C back here. So it's harder to visualize. This is easy one. But the hypotenuse is 2 feet and the angle is 20. So I'm going to, green, this, and I'm going to indicate that this is 2 cosine 20. Visualize. And this is 2 sine 20. The hypotenuse is 2 feet. And the angle is 20. Alright, So the distance from A to B for you indicate AB is going to be, in the x direction it's going 1.5 feet, and the angle is 20. In the y direction, it's going negative from 2 to 3, so it's only negative 1 foot. This is, alright, so the distance from A to B in the z direction is going down 4 feet. AC. So the distance A to C, it's going A to C. Well, in the x direction, it's going backwards, so negative 2 sine 20. It's going to be, in the x direction, it's going 1.5 feet. In the z direction, it's going down 4 feet. In the y direction, it's going over 2 plus 2 cosine 20. So that would be positive direction. In the z direction, it's going down. X direction, it's going backwards. So negative 2 sine 20. And then in the z direction, it's just negative. In the y direction, it's going over 2. X direction is going to negative. We need to figure out the resultant force. So, force AB is going to be FAB direction. It's going over U vector AB over U AB. So FAB is going to be, let me put this into a calculator, FAB, which I did not write down yet, but the book tells us that FAB is 20 pounds. Times U vector AB, I'm going to use the x component, negative 2, nope, the AB, not BC, which is 1.5, FAB over the square root, 1.5 square, plus 1 square, plus 4 square, 20 pounds, is going to be, put this into a calculator, okay. That gives me 6.84 I, it's 20 pounds. And I'll put negative 1 into the numerator. 1.5 square. I'm going to use 4.56 J. Put negative 4 in the numerator. 1.5. Okay. That gives me 18.2K squared. F squared plus 4 squared. AC. So now the denominator becomes, well, first of all, FAC, according to the book, 40 pounds. So it's 40 times. Now in the denominator, I'm putting negative 2 sine 20 squared. Now the denominator becomes 2 plus 2 cosine FAC 20 squared. So at 40 times plus plus 4 squared is 16.
Welcome to EDU World Space.
Alright, so the numerator is negative 2 sine 20 plus negative 4.87.
So to begin,
Now I'm going to put the 2 plus 2 cosine 20 in the numerator.
dA equals the total charge inside divided by L.
27.6.
We can see that the electric field equals K inside divided by R squared.
And now negative 4
K is just a constant, not a number.
in the
You can
numerator.
also write the terms of this one. Okay, so let's find the
I
electric
need to
field.
add those together to get the result.
2 plus 2 cosine 20. There is no charge here. If there is no charge,
6.84 minus 4.87 1.97 pi.
what about in between all of the first
27.6 minus 4.6. 1.56.
So, there's no charge on one side.
23.
B less than R less than C. In this first ordered region.
18.2 plus
Has
28.5.
equals 2Q. And so that is what would be Q equals to. Okay, so it's plus 2Q. So that means that the electric
And we're still not done.
writing it like it. 1 divided by 4 pi epsilon 0 times the total charge inside, which is 2
This equation.
divided by R squared.
27.5. That in no calculator.
And let's see now. C less than R less than B, so now we're in this outer region. Okay. So in this outer region, I know that the electric field must be equal to 0 because when we're at
52.1.
so that is 2Q here. So we need minus 2Q on this intercept. But in general, still because we are inside the conductor. And finally, when we are outside the system, all we have to do is take the total charge times RT inside.
Check if that's the correct answer.
So divided by minus 2Q.
Yes, it is.
E equals 1 divided by
And then to get alpha, beta, and gamma, we just use the inverse cosine
2Q
of FR X, which is 1.97, over FR, which is 52.1.
Right?
Putting that in calculus.
And what do we see? 0, 0. Here, 0 is there. Between B and C. Yes, we can see
87.8 degrees. Beta. Just have to change the numerator
now
to 23.
So even though
Gamma, I changed the numerator to negative 46.7.
see what happens when you outside your expression of your
Numbers are correct.
So I'm not going to try to see what happens when you have a negative sign outside the expression.
Gamma, I changed the numerator to negative 46.7.
It looks like when you graph it, there will be two solutions, and if you're going to choose the physical solution. And so, in this instance, it would be something like Okay, so now we can look at the charges that are around these shells. Okay, let's look at the inner surface of our small. The inner surface of our small. Remember, electric field must be 0. There's nothing wrong with the very inside of this guy, where that green dot is. So, this guy must be 0. But on the outer surface must be the total charge of the shell.
Is going in the y
Okay,
direction.
this is a large one. Okay, on the inner surface, we need to have an electric field 0, so it has to cancel the total charge from this inner shell. So we need a negative 2 here on the inner surface. Okay, so now and then okay, the outer surface.
I don't know why we even use it.
Face off. Okay. Well, there's minus 2 right here.
I'm going to go ahead and say right now.
So what has to be
Now
is out here.
it's going to be 90 degrees.
Minus 2 here. Outer surface. It's the only way for the net charge to be like this.
This is only one part. What is
Okay,
it?
on the inner surface, we need to have an electric
Easy. Okay. This is really just a two-dimensional problem.
Okay, so
I'm going to treat this as a two-dimensional problem. This, by the way, is the third.
Welcome to EDU World Space.
okay, so we have two concentric shells, and a radius A, a radius B of our inner shell, and a radius C, a radius D of our outer shell. The inner shell has a total charge of 2Q, the outer shell has a total charge of minus 2N, and we're going to find the electric field from there, and where the charges are. Let's get started. So remember that when you have a point charge, the electric field is given by this. Remember what K is? K equals 9 times 10 to the 9. It's also equal to 1 over 4 pi epsilon. Epsilon is just a constant. Also remember Gauss' law. Gauss says that the closed loop integral of U dot dA equals Q, the total charge enclosed divided by epsilon. Alright, so first region, radius less than A. Okay? We are right here in this little green dot. We have no charge there. With no charge, Q is 0, so E must be 0. Okay, A less than R less than B. We're in this inner shell first, or smaller shell. This is a conductor where the properties is that E equals 0 inside of it's also equal. So let's type 0. B less than R less than C. So now we're in this first one, it's just a constant. Well, what is the total charge in that region? Also remember those plus just the charge of that inner shell is 2Q. So now we can just imagine that it's a joint charge and say that the electric field E equals 1. Right, so first region, radius less 4 pi epsilon. Okay. Times Q, total charge inside. We have no charge. 2Q over squared. So Q is okay. Alright, now we're in our outer shell. C less than R less than D. C less than R less than D. Well, do our Gaussian surface. We're somewhere here. What is the total charge in here? Well, it must be 0. Why is that? We're inside of the conductor. Again. So, E equals 0. There it is. Not bad. Now what happens if we are outside of that? So now what happens if we are doing the Gaussian surface outside of these systems? Well, what is the total charge enclosed? Plus 2Q minus 2Q, that equals 0. Times Q plus 2Q here as well. So we can go ahead and graph this. 0, 0. So we have these regions of 0. Right. B to C.
Well, if alpha 1
There's
and
something
beta
like this.
1
It's going to R squared. And then it goes straight back to 0.
Beta 1.
Alright, now let's look at where these charges might be located. So, what is the charge on the inner surface of our smaller sphere? Or smaller shell? So, if we are looking at this region right here, well, we know that the electric field must equal 0 here. There's no charge on the inside here, so we can reduce these two values. What about the outer? Go right here, plus 2 minus 2. Well, what is our charge when it goes here? Plus 2q. Everything is in there. So the electric field due to a plus 2 V to C charge. Plus 2q. What about our large shell? Right? We go right on this inner diameter, right here. Okay, we know that the electric field must equal 0 here. That means it needs to cancel with this plus 2q that's happening right here. That means all of the minus 2q is going to hand this minus 2q. Then what about this outer surface?
Oh, note that I've realized this one.
We have a net charge of 0 here.
Alright.
Plus 2q.
So, that doesn't make sense now. Not.
So, the outer
now, this
must equal 0.
after I get those signs,
We go right on
Eight.
the diameter.
okay. And F R
That means it needs to cancel this plus 2q. That's happening here. That means all of the minus 2q
is negative 350.
Welcome to EDU World Space.
Okay, so for this problem we have an inner shell and an outer shell. And the inner shell has a charge of plus 2q, the outer shell has a charge of plus 4q. The inner shell is bound by the radii A and B, the outer shell is bound by the radii C and D. We're looking for the electric field everywhere and see if we can find where the charges are going. So let's go ahead and look for the electric field everywhere. So, in order to find the electric field, we're going to write down Gauss's law of 3, which says that the closed line integral of v dot dA equals total charge that is enclosed in our region divided by epsilon 0.
Alright.
So in general, this is our Gauss's law. And this is our area element. This is our total charge enclosed in our Gaussian surface. This is epsilon 0, just a E, and E is what we look. So let's look for our first region, which is when we have a radius less than 3 and see. So for or less than A, well, we don't have any charge there, so that means that Q equals 0, Q equals 0, E equals 0. So in order to find the electric field, we're going to write down Gauss's law of 3. That the E equals the integral of v dot dA, this region. Alright, what about if we are in between A and B, so now in this shell right here, divided by, well, if it is a conducting shell. Then, by definition, it must have 0 electric field. So they're the same thing. E must equal 0. So let's look for our first region, which is when we have a radius of less than 3. Now what about this cavity between B and C? And so for B, that means less than R, and C, E. Well, now we do have some charge. We have the total charge on this shell, plus 2q. So just in general, we know that the formula for the electric field of a point charge equals K, which is 1 over 4 pi epsilon 99, KQ,
Now,
it must have divided by r squared.
gamma.
We can use this for our region between B and C, and we see that the electric field E equals
Anyway, we'll figure this out.
now K, which is 2 Q right here is the total charge divided by r squared. R squared is just the total charge of this shell plus 2Q. We can write this more explicitly. 1 divided by 4 pi epsilon times 2Q over r epsilon 99. Okay. Now what about the region C and D? So now we are in this outer ring. Well, when we are in this outer ring, remember that the electric field must equal 0 because it is a conductor. So, for the region between C, K less than R less than D, to E equals 0. Q right here is this total charge inside that conductor. R squared. Okay, and then finally, what about if we are outside of this object? So what happens if R is greater than D? Well, when R is greater than D, then we have the total charge enclosed, which is 4Q plus 2Q, 6Q. So we just can use this formula right here for our regular charge, and we get our electric field is E. Remember, the electric field equals 1 divided by 4 pi. So, for the region of epsilon 0, C times 6Q E over r squared.
I've got 3 under.
Okay. And then finally, what about the equations? Those are all of our regions. Now we can go and graph this. So if we wanted to graph it, it would look something like this.
Which means that I have 4 equations.
E,
4 equations.
And we have
unknown.
A. So it would just be right here, C,
I
D,
can combine some of them together.
and we get field E. Okay. And we are going to get,
Let's just go with the last one, the second one. This one.
and
That's
what
going to
about
say that the cosine of gamma 1
times 6Q
mean that I have
originally 0 because we have no charge inside of that inner function. And between regions B and C, here's our formula.
cosine gamma 1.
So it goes as a 1 over r squared. So if we wanted to graph it like this,
Okay, good.
and
You know what? I could
we
solve
see a similar function for when r is equal to D. Well, this time we are going to have a different prefactor in front, and it's going to be okay, like that. And we are going to
400 sine 30.
and so that's that. Now, what about the charge on the inner surface?
First, okay, good.
Originally,
Cosine alpha 1.
well,
Inside
of that inner
sine 30.
Okay, so the inner surface, what's the total on the inner surface of this solution?
Going to be
Because it's 1 over r squared, it has to be 0.
negative
Why is that?
200.
Because the electric field is 0 and we have a Gaussian surface right there. So I see a similar function for the Gaussian surface. We have a charge right there, there's this, on the inside is 0. We are going to have a different zone in front, inner, and
I can substitute 400
inner
sine 30.
is 0. minus 19th place.
the last equation, and that's going to give me negative
Okay, what about the outer?
over F1
All the outer surface right here.
plus
Okay, so it needs to contain all the charge for this inner shell. So it has to be plus 2
cosine
q.
30 over negative F1
Okay, and what about for our large?
plus 400 sine 30
Okay,
over
with the inner.
squared 1.
So we do a Gaussian surface right here.
And multiply by F1 squared on both
We know
sides.
that we must have net 0 electric
And
field.
just say that that equals F1 squared.
The only way for that to happen is that there must be a reduced negative 2q charge on the
Both
inside. It needs to
sides.
contain
That would be what
so there's
F1
no
is.
negative 2q.
So F1
Why is that?
would
Because
be,
you need E net to 0.
put it in here,
Okay?
a lot of work.
Outer surface,
Square root
or Gaussian surface.
negative 350
That's just the total charge, 4 plus 2.
squared. Plus square 100 minus 400 cosine 30
And
squared.
that's that.
Plus 400
Also, another thing to
sine
note with Gaussian's graph
30
is that this is, if you were to have units on this,
squared.
you would expect that this would be a bit taller than this. Because this is 6 divided by 4 by 2.
That gives me 429 squared.
This is the way it's
Let's see if this is right. 71.
And that's that.
Yes, it is. Except it's not newtons. Count.
Outer surface.
Square root 30.
That's just the total charge.
So now I just need
Welcome to EDU World Space.
gamma. That should be pretty easy now that I know that's 429. So
This is
the inverse cosine
to have units on this. You expect that this would be
of alpha is going to be 400
taller.
sine 30
This is 6 divided by 4.
over F1. That's 429. This is right. Now, so alpha is going down 62.2 degrees. Beta is going to be the inverse cosine, but in the numerator, I need to put 200 minus 400 cosine 30. So now,
Welcome to EDU World Space.
It's going to give me 110. So, inverse degrees, and gamma is just going to be negative 350. Beta is going to be the inverse cosine over. Good, and that would be obtuse. 1. Check those answers. Gives me 100. And that is correct. I'm a little bit surprised that I didn't make any mistakes. That was pretty complicated. 200 minus 400 is just going to be negative 350. Give me 100, that would be obtuse. In here. I'm surprised that gamma of the 3 forces. However, negative 350 you're basically going to have to get the resultant of some, and that would be obtuse. Y, X, Z. And so, however, and that is correct. I'm a little bit surprised trying to see what's going on here. I think I may try to do this direct, and so what's going on. However, I think EA try to do this direct, and Y X B, and so C is here. What's going on? A up here. I think I may try to do this direct, and so what's going on here? I think I may A up here. Okay. So let's try to get FBA first. I see that in the X direction. Okay, you can see a lot of measurements. So let's try to get what I'm gonna do is use. So let's try to get F here. BA. And we go until we get to the z-axis. Then we can see from B to A that the distance. So if we start here is show this. This distance here is 3 plus 2, which is 5 feet. And so UBA to the vector from B to A is going to be, well, it's going -5. The distance here in the I direction is 3 plus 2, which is 5 feet. It is going 6 is 3 plus 2, 5 vector from B to A. So it's going to be in the J direction. It's going negative from B to A. And it's going upward. They're all doing the same thing in the K direction. They're all going up 14. The I and it's going upward. Well, from C, all going up, and it's going X direction. It would be negative in the X direction, -3. This distance here is -3. Well, from in the Y direction, positive 3 to get to the Y. Negative in the X direction, -3. And in the Z direction, they're all the same. It'll be negative in the X direction, -3. UDA in the Y direction is from B to A. X, Y to go. And in the Z direction, they're all the same. And in the Z direction, they're all the same. Wait. Let's go back to BA. From B to A, you have to go negative.
Welcome to EDU World Space.
But from C to A, in the X direction, you have to go positive. This should have been positive. I'm going to think about whether I messed up my negatives and positives. So let's go back. From B to A. B, A. Let's go back to X. B to A should be negative, Y
find
should be
also we
positive.
have to be
Let's go back to B. C to A.
and we found this
Positive X.
Welcome to EDU
Positive Y.
Workspace.
Positive Z. Okay. I'm gonna think about whether it wants to be B to A right now. So let's go back. B to A. It is going negative in the X direction. So this distance here is 5. Okay, negative 5.
draw a circle.
It is going negative in the Y direction. It's also going negative. This distance here is negative 6. Negative in the X direction. Negative 5.
And this one is to be
express each force as a vector. Okay, so I'm going to do this. Force BA vector.
So for the F11 is just the average
force BA 350 times U BA.
F12 is just
This over force magnitude of UBA BA vector. So let me get that using a calculator. Force BA 350 times
now for the
FBA was 350 over force magnitude. FBA is 350. So let me get that using a calculator. Force times UBA in the X direction is going to be negative 5. FBA over was 350. Square root. FBA is 5 squared over, let me get that, force magnitude squared. So let me get that using a calculator. It's going to be negative 5. And so that would give me negative 109 square root BA. I'm going to check the answers to make sure I'm on the right track. Yep. And I also wanted to check how many digits it is. Negative 109i. Now all I have to do is put positive 6 in the numerator. Check the answers to make sure I'm on the right track. 31J.
Welcome to
Now I need
EDU
to put
Workspace.
positive 14 in the numerator. Negative 109i. 306 so I can, in the same manner, get FCA. Now I need to put F so for CA, the denominator 109i would be 3 squared. Now all I have to do is plus 3 squared. I can, in the same manner, 4 squared. 14 squared.
Welcome to EDU Workspace.
FCA for CA is 500 pounds, 3 squared, 500 in there. And the numerator is 3. Same matter, FCA. So that's going to give me FCA 103 plus pounds. It's also 3 in the J direction. 103 J. And then in the K direction is 14 again, so
in our circle,
numerator
it will be 60 degrees.
479.
60 degrees counterclockwise.
And let's get the last one. So negative 5 squared is 25. Negative 6 squared is 6. And 14 squared is 196. And the numerator is 3. The force in the D direction, FDA, is 400. And let's get the next one. One calculation, negative 5 squared. And the numerator is a negative 5. Gives me negative 125. Second numerator is negative 6. 400. Negative 150. And let's get the last one. So negative 5 squared. J. And 14 here. Second numerator is negative 6. Check the answers. This is problem 95, and A looks right. B looks right. CA looks right. Check the answers. I don't know what's going on with this is DA. My answers aren't even close. For DA, negative 52.1. Negative 156, 356. I don't know what's going on. Okay, so what did I do wrong on DA? Negative 52. So DA, negative. Just go through exactly what I did again. From D to A. It's going negative 6x. It's only going negative 2. It's going negative 2 in the x direction. It's going negative 6 in the y direction. That's supposed to be 2. So that should change everything, actually. That's going no. Okay, so DA is 2. From calculator, it's going 2 squared is 4. And in the numerator, I had negative 2. That gives me 50. Okay, so DA is 2.
Welcome to EDU World Space.
Negative 52i.
So in this question we have to use
is
state of
negative 6, I
that we
believe.
are right? So in this we use negative
Minus 156j. And the third one is 14 in the numerator.
Acting on the y direction is equal to 550.
Okay, let's see if that is it.
And the
And I'm in question 95. Negative 52, negative 156, 365. So my error was in reading the graph. This is not 5.
Now we are going to use the Mohrs.
Okay, let's see if that is. I was confusing the edge of the plate of y-axis.
Right, and for that we are going to put the circle and
distance
for
the
that
other
we
plate
use
is
x
5. The distance here is 2, and we want to use 2.
Right, so we have force here that is equal to x minus y and every value of the screen. Right, so and that is
No, I don't understand why 66 comes after 65. 66
Right now,
is so
all
much
we need to
easier.
do is
I
that
already
we need to
have
find out the radius of the
components
circle, and we have a description for this
and so, if I
radius as
do
well,
180
right? We have
angles, all I have to do is write that alpha is the inverse cosine of negative 106.1 over f1. Beta would be the inverse cosine of 106.1 over f1. And gamma is the inverse cosine of 259.8 over f1. And we know that f1 is 300. So let me put those in the calculator.
Now, as you can see over here, that this is
cosine
at which the rate of speed is upstream, right? So we need to measure the angle from this point, right? Now the principal streams are easy to find, right? Because we can see her closer. Now for that, principal streams is off, right? You have to have this question something new. Can you get that right? And the other principal string is 9.8. That's alright. Again, you have the values, just plug them in, and you have your values. You also remove time, right? Into energy of negative 6. Right, now that you have the values of this domain, we need to find out the maximum in plane shear strain, right? That is given by this divided by C, that is equal to R. Right, so when you shift this
It's a continuation of the previous problem. And they're actually only asking us for the two forces acting at point A. So I don't do anything with this. All I have to do is add these together, the continuation as and the resultant is going to be
right now, since the principal streams, they have the same sign, right? They have the same
they cancel each other out in J. And in K, 195 times all I have to do is
can directly have the expression for the maximum value of
390.
the shear strain, right? That is the maximum
Continuation. And they're actually so, the resultant is just going to be the square root of negative 648. So all I have to do is add these together. Square root plus 90. What it's going to be.
Welcome to EDU World Space.
Putting that in the calculator.
So let's solve this question. So in this question we have silent x here.
640 negative 648.
Minus square plus gamma xy.
Squared is 750.
Following this, silent x equals to epsilon y.
756. What are my units?
Gamma xy.
I hope this is correct. Check. 7. 640. Yep. So now alpha, beta, and gamma. Obvious.
Now we have x, y, s.
Alpha is going to be the inverse cosine of negative 648 over 756. And now beta is equal
minus b minus 3. So that is tau xy s plus equal to now we have tau xy is to g gamma xy. So this is
149 degrees. Beta is going to be 95 because there's nothing in the y-axis.
E comes out to be 80.05.
And yeah, this was okay. Gamma is going to be, I need to put 390 in the numerator. 59 degrees.
Welcome to EDU World Space.
So in this question, the radius is right, the material that is visible here is the tangent that is provided is right, and we are required to determine the
I'm going to begin by drawing a diagram as usual.
Now, the thing to note over here is that as there is no load that is applied over here, right? So it means that if there is
Okay.
torsion present, and as there is only torsion present, so it means that there would be
Got a force.
It means the stress of the x direction is equal to stress in the
This
y
direction.
0, right? And if there is no stress, it means that there is no normal strain, right?
Force
So
is here.
it means that the strain in the x direction is 0, right? So now since this is
We're
a
told
zero,
that
let's write the strain Rosetta equation for 45 degrees, right? Strain
Minus
Rosetta
250 J minus 450 K. And we know that the length right here is 9 meters. So the first thing that I want to do is I want to find the direction of the force, which is just going to be the force.
Zero right is
divided by the magnitude of the force.
Sorry, gamma of x minus
Force.
right, so let's say the equation again. Now what we do is that we write the equation.
So, let's go ahead and get that.
So 40.
So, x component is just 2 to 3 to 50.
Right, so now what we need to do is that
Square root is 50 squared. Is 250 squared. Is 450 squared. Divided by magnitude. That gives me an x component of 0.5
so again, these two terms would become 0 and 2. And solve it and you get that it is equal to
now I'm going to put negative 250 in the numerator. It's negative 0.402
right, with the
J.
torsion maximum is
And I'm going to put negative 450 in the numerator.
and because that torsion is equal to
0.73
and we solve it for gamma, right? And we
now,
for gamma, we get this.
If I take
right? So what you're going to do over here is that
you
plug in the value and you get
multiply it by 9,
right?
that will give me the distance vector.
Positive
X, Y, which would just be the X, Y, and Z coordinates of point A, except it would be the opposite of the X, Y, and Z coordinates of point A. So X is just going to be 9 times 562. Y is just going to be 9 times negative, no, it's the opposite. So it's going to be 9 times, it's just going to be 9 times 562.
Welcome to EDU World Space.
9 times y negative 0.40 and z is just going to be 9 times 0.723. 9 times. So put these in the calculator. It's just going to be 9. The z is 6.51. And what are our units here? Meters.
What you're going to do over here is that
is 3.61 meters.
right?
Units here. And meters. Negative 5.06. Let's check this calculator. 89. 5.06, 3.61, and 6.51. So the only difference is it incorporates as x is positive 6, but I wrote that x is negative. I guess they're showing x to be in the opposite direction of the x-axis, and so okay, that makes sense. Very good. Negative 5.06.
Under root, the distance of the plane is
Welcome to the channel World Bus Navigation Guide. Time to synchronize step-by-step solution that solves today's problems together.
Okay, so let's define the angles of the chains with respect to the horizontal axis. On the background, we can see that the maximum chain area has a horizontal axis is 40 degrees, and the angle between the chains using an horizontal axis is 60 degrees. So let's calculate the horizontal and vertical components of the forces. For chain AB, horizontal component is FAX equal to FA times cos of 30 degrees, which is equal to 300 times cos of 30 degrees, that is 150 times root 3. Similarly, we have vertical component FAY equal to FA times sine 30 degrees, which is equal to 300 times sine of 30 degrees, that is 150 Newton. Now for chain CD, the horizontal component will be FC equal to FC times cos of 60 degrees, that is 250 times cos of 60 degrees, which is equal to 125 Newton. Immediately we have vertical component FCY equal to 125 times square root of 3 Newton. Now express the forces in Cartesian vector form. Force AB in Cartesian vector form is equal to 150 times square root of 3 times 150 J Newton, and force CD in Cartesian vector form is 3 force 2, 125 is 125 times root 3 J Newton.
Now we need to find out the other principal traits. Insect passwords plus
Welcome to the channel where we ask complex questions and break them down into simple step-by-step solution that solve today's problems together.
Now, at least this diagram seems easier to see. It's a little bit harder to interpret, though. Let me go ahead and draw. This is what I can draw here. At least this diagram seems easier, which I would draw on the y-axis. C. Let's try again. Okay, so continue this through. We've got a point B down here, which looks like the easy one. Definitely the easy one. There's a point A up here. C. And we're shown that this is 3. Continue this through. This is 4. This is 2. I guess that's it for that one. Up here. Oh no. This is 1.5. These are all feet.
Right now, circle vertical tree is the house.
And then there's a point C back here. It's harder to visualize. But the hypotenuse is 2 feet and the angle is 20. So I'm going to green C back here like this, and I'm going to indicate that this is 2 cosine 20. This is 2 feet.
Welcome to EDU World Space.
And this is 2 sine 20. Alright, so the distance from A to B
So, to begin, we need to write down Gauss's law.
for you
Cosine integral
the hypotenuse is going to be, in the x direction is going to 1.5 feet.
We can say that the electric field equals KQ.
In the y direction, it's going negative.
You can also write it in terms of Gauss's law.
From 2 to 3, so it's only negative 1 foot. 2 cosine 20
Okay, so
is going to be in the x direction. In the z direction, it's going down 4 feet. This is in the y direction. AC. Distance from A to B
about in between
A to C. A to C. Well, in the x direction, it's going backwards, so negative 2 sine 20. In the y direction,
or in a
it's
shell
going over 2 plus 2 cosine 20. That would be 2 sine 20, the positive direction.
So that means that the electric field can be written as a potential writing
and then in the z direction, it's just negative 1.
Temperature charge inside, which is 2Q, divided by and let's see now.
We need to figure out the resultant force. So, force
FAD,
FAD vector AB over U. AB.
So we need minus 2
F AB is going to be, let me put this into a calculator, FAB, which I did not write down yet, but the book tells us that FAB is 20 pounds. Times U vector AB, I'm going to use the x component, negative 2, the AB, not the C, which is 1.5. Over the square root. 1.5 squared plus 1 squared plus 4 squared. Okay. That gives me 6.84 squared.
Even though that this is
Now I'll put negative 1 into the numerator. 4.56 away. Put negative 4 in the numerator.
your expression now. So
18.2k plus 4 squared. F.
To see what happens, we have a negative sign
AC. So now the denominator becomes, well, first of all, FAC, according to the book, it's 40 pounds. So it's 40 times. Now in the denominator, I'm putting negative 2 sine 20 squared. Plus 40 times 2 plus 2 cosine 20 denominator.
Okay, so now we can
Square.
these shells. Okay.
Plus 4 squared.
The intercept of our sine.
Alright, so the numerator is negative 2 sine 20.
So
give us negative 4.87.
Outer surface.
Now I'm going to put the 2 plus 2 cosine 20 in the numerator.
Okay. So the large one.
27.6.
We need to have more. So it has to cancel.
And now negative 2.
Negative 2. Okay, so okay. And then what's out?
Now I need to add those together to get the result.
The outer surface.
6.84 minus 4.87.
This 2 here.
1.97i. 27.6 minus 4.56. 23. 4.7. 18.2 plus 28.5. Add those together by the result. And we're still not done.
Welcome to EDU Workspace.
17.2 shells. This equation. Put that into a calculator.
So remember that when you have a point charge, the electric field is given by this equation. K equals 9 times 10 to the 9. It's also equal to 1 over pi epsilon. Epsilon is just a constant. Also remember Gauss' law. Here it is.
Not pounds.
Gauss. It says that the closed loop integral of E dot dA equals Q, the total
Check if that's the correct answer.
Alright, so first
Yes, it is.
radius less than A. Okay?
And then to get alpha, beta, and gamma, we just do the inverse
We
cosine
have no charge there. With no charge, Q
of
is 0.
FR
So E
X, which is 1.97, over FR,
A
which is 52.1.
we're in this thin
Not
shell,
in the calculator.
smaller shell. This is a conductor. One of the properties is that E is 0.
Inverse cosine.
B less than R less than C. So now we're in this first loop. What is the total charge in that region?
7.8 degrees. Beta. Just have to change the numerator to 23.
And say, alright, so radius less than 1.
Gamma, I changed the numerator to negative 46.7
times Q total size 2Q over squared Alright,
and here's our current.
C less than R less than D. C less than R less than D. Negative 1 so I got some surface. What is the total charge in here? Well, it must be 0. Why is that? We're inside of the silicon. So, E is 0. Now what happens if we were outside of that region? So now what happens if we are in the Gaussian surface? Well, what is the total charge of this? Plus 2Q times minus 2Q. That equals 0. E equals to 0 here as well. We can go ahead and graph this. 0, 0. So which is B to C. Goes something like this. Squares. And then it goes straight back to 0. Alright, now let's look at where these charges might be located. So, what is the charge on the inner surface of our surrounding sphere, or small shell? So, if we are looking at this region right here, so now, well, the electric field must equal 0 here. There's no charge inside this reduced to the right here. Well, what is our charge when enclosed here? 0. Plus 2Q. B to C. The electric field gives us plus 2Q charge. Plus 2Q. We've got our large shell. We go right on the inner diameter. So we know that the electric field must equal 0 here. That means it needs to cancel with this plus 2Q that's happening right here. That means all the minus 2Q is going to land at the surface. Minus 2Q. And what about this outer surface? It's got to be 0. So we have a net charge of 0 here. So the outer must equal 2
don't know what is different, seriously.
Welcome to EDU World
This
Space.
is 30 degrees.
Okay, so for this problem we have an inner shell and an outer shell. And the inner shell has a charge of +2q, the outer shell has a charge of +4q. The inner shell is bound by the radii A and B. The outer shell is bound by the radii C and D.
Magnitude and direction.
Looking for the electric field everywhere and see if we can find where the charges are going. So let's go ahead and look for the electric
X
field.
direction is going to 400.
So, in order to find the electric field, we're going to write down Gauss's law, which says that the closed line integral within the dA
is going to
equals total charge that is enclosed in our region divided by epsilon 0. So in general, this is our Gauss's law, and this is our result. Of course, this is our total charge. And E is y. So let's look for our first region, which is when we have a radius less than A. So for r less than A, well, we don't have any charge there, so that means that Q is 0.
put all of these in
0.
your calculator. So know exactly where that data is. And so,
Alright, what about where you're in between A and B, so now we're in the shell right here. Well, if it is a conducting shell, then by definition, it must have 0 electric field. So we have the same thing. E will equal 0 here. So, now what about this cavity between B and C? So, for B less than R, C. Now we do have some charge. We have the total charge on this shell plus 2q. So, just in general, we know that the formula for the electric field point charge, E, well, equals K, which is 1 over 4 pi epsilon, or 99, K Q, 0, divided by r squared, we can use this for our region between B and C, and we see that the electric field, now what about the total K, Q, which is 2 over Q right here is the total charge divided by r squared. R squared on this shell is just negative. So, I'm writing more explicitly. 1 divided by 4 pi epsilon.
So we're supposed to measure
K, which is comes to Q epsilon over Okay. Now we've got the region C and D. So now we are in this outer ring. Well, when we are in this outer ring, remember that the electric field must be 0 because it is a conductor. So, for the region between C to less than R less than D, Q right here is E.
We've got 3 forces.
Inside that conductor. Okay. And then finally, what about if we are outside of this object? So what happens if R is greater than D? Well, when R is greater than D, then we have a total charge enclosed, which is 4Q plus 2Q. Now it's Q. So we just need this formula right here for our charge, and we get our electric field E equals, so 1 divided by 4 pi C epsilon 0
Angles
times the 6 cubed those are all of our origins. Now we can go ahead and graph this.
So we need all three forces in Cartesian vector form. So F1
and we have
is going to be. It's going to have an X component. It's 50.
And we are going to get
X direction in 3 directions.
And what about between C and D?
Y component is going to be 50 times 4/5.
Originally, 0, no charge. And inside that inner shell.
F2.
And between regions B and C is so
X
because of the 1 over R squared,
this sine,
and we see a similar function for when R is greater than D.
and also
However,
negative.
this time we are going to have a different vector and it's going to be
X direction
like that.
F3.
And so that's that. Now, what about the charges on
30 X direction.
Inside
Well, alright.
okay,
I
so
think I'm going to leave it like that.
the inner surface, what's the total charge of the inner surface?
Determine the magnitude of the resultant force and the direction.
Has to be 0. Why is that? Because the electric field is 0. C is similar when we have a Gaussian surface right here. So this
X direction
this time is surface. Charge right there, there's nothing inside.
3/5 of 50. That's only going to be 30.
Inner
Minus F3 sine
inner is 0.
15 plus X
Okay, what about the outer?
50 times 4/5 is 40.
All the outer surface right here
Minus
to contain all the charge for this inner shell. So that's 2Q.
Let's go ahead and get that.
Okay. And what about for our large?
30 minus 3/5 sine 15
Inner.
plus 30.
Okay. Got the inner. So we do Gaussian surface right here.
40 minus
We know that we must have a net 0 electric field. All the outer surface right here. The only way for that to happen is that there must be an induced negative
to do the Pythagorean theorem, so I'm going to take in the square root
So it has to be negative 2Q.
of the first one squared
Why is that? Because we need E net T for 0.
for x squared
On the outer surface,
for y
or Gaussian surface, that's just the total charge, 4 plus 2.
right one squared 54
And that's that. Also, another thing to note about this graph is that this is, if we were to have units on this, we would expect that this would be, there must be a bit taller to do the
Pythagorean theorem.
This is 6 divided by 4 pi, and this is 2. And that's that.
43 degrees. It says clockwise from the positive x-axis. So that's going to be the opposite of this, and that becomes 43.5 degrees. 54 newtons at 43.5.
Welcome to EDU World Space.
43 degrees.
This is
clockwise from the positive x-axis. don't know, so far this section seems to be exactly the same as the previous section. Don't know what is different, seriously. So, we're showing that this is 30 degrees. We're also showing that this down here is 45 degrees. But I would rather mark this as 45 degrees, and it would be 45 degrees because it's a right angle. The magnitude and direction of the resultant force. Well, force resultant in the x direction is going to be 430 plus 800 cosine 45. Force resultant in the y direction is going to be 400 sine 30 minus 800 sine 45. The resultant force is going to be the square root of f squared plus f y squared, and the angle is going to be the inverse tangent of x direction y over f. The resultant force is going to be the square. Put all of these into a calculator. It's important that you do the first two so that you know exactly where that theta is, whether it's downward or upward, and so go into a calculator. 400 cosine 30, 800, the resultant 5, 912, and this is Newton. Okay, next one. And calculate 400 sine 30 minus 800 sine 45. Negative 366. All of these are calculators. First two, exactly where square root. Downward the first one, and so calculator plus second one, 430 squared is 983 newtons. And theta is the inverse tangent of the second one, or the y direction. Over the x direction. And theta square root is the inverse tangent of the first one, negative 22 21.8 degrees. So we're supposed to measure clockwise from the positive x-axis, so that would be correct. These two are my answers. Let's check. And the book, 983, 21.8. Yeah, it would be positive 20.8 as measured from in the clockwise direction. We're supposed to measure clockwise from the
Hello and welcome to this video solution of numeric. So here we are given that the board is subjected to a that has component vector along x, y and z axis as shown here. The force is 80 meters and alpha is 60 degrees and gamma is hello and welcome to this video solution. So based on this you have to calculate the magnitude of its components. So clearly if x component is not equal to cos alpha plus this is equal to 8 cos of 60 degrees right. This is equal to 40 meters. Next, if you move on to the second component, then y, and that is equal to cos, z component because beta is not given. So z will be equal to cos gamma, right? These two components are and this is 56.6. So based on second calculation, now to calculate is y, what is the real if we do the rule of second z square y square plus z square is this is 80. That will be equal to x is 40 square and this is y is calculate with everything calculation is 6 and y will be 40 is what we have. So you have got all these components. I hope this is clear to you and I will rest of the day. Thank you.
I don't know, so far this section seems to be exactly the same as the previous section. I don't know what is different, seriously. So, we're shown that this is 30 degrees. We're also shown that this down here is 45 degrees. But I would rather mark this as 45 degrees, and it would be 45 degrees because in all it's different. It's right angle. What's the magnitude and direction of the resultant force? Well, force resultant in the x direction is going to be 430 plus 800 cosine 40. Force resultant in the y direction is going to be 400 sine 30 minus 800 sine 45. The resultant force is going to be the square root of F(r)x squared plus F(y) squared, and the angle is going to be the inverse tangent of y over F(r). So to put all of these into a calculator, it's important that you do the first two so that you know exactly where that theta is, whether it's downward or upward from the horizontal. And so, go into a calculator. 400 cosine 30 plus 800 cosine 45 912
Our inner shell has
okay, next one. 400 sine 30 minus 800 sine 45.
So that means that the electric field
negative 366 newtons.
writing it like that, we get 1.45
square root.
comes to a charge inside, which is 2q divided by r
squared plus second one 300.
And let's see now. C less than r
squared is 983. And theta is the inverse tangent of the second one on the y direction.
But
over the x direction.
And finally, we are outside of the system inside.
Negative 22. 21.8 degrees. So we're supposed to measure clockwise from the positive x-axis, so that would be correct. Those two are my answers. Let's check in the book. 983, 21.8. Yeah, it would be positive 20.8 as measured in the clockwise direction.
Between B and C.
This problem together.
C.
Okay, for this problem, we have a plate that has 4 different forces acting. Force 1, force 2, force 3, force 4, and it actually gives us magnitudes and this for each of these.
Now, remember these instructions that even though the
Force 1 and force 2 from 3, 4, 5 times just to y-axis. And so using these, we have to actually find the resultant force vector and show that the resultant force is 0. So we can do this by determining the x and y components and summing each of them individually to see that they both add up to 0. So let's start with the force vector, the explanation. Because we're applying magnitudes, and we can determine the components based on these 3, 4, 5 triangles. We can these triangles individually. So this one right here is the triangle that F force 1 forms with the y and x axis. And this triangle on the right side is the one force 2 forms with the x and y axis. So we start with force 1. So for the first triangle, we're going to be using right angle trick, so SOHCAHTOA, to determine what purely horizontal components. So here, because we need to find the horizontal side, or we use cosine in SOHCAHTOA, which is adjacent over hypotenuse. So here is going to be right angle trick.
okay, so
times 4 over 5. Force 2 plus,
let's look at the
here it's going to be, so once again, that force 3 over 5. So it'll be 6 kilonewtons, F2. And we can just add, so we should just subtract force 3 and force 4. Because if you notice this diagram, both ends are going in the opposite direction horizontally, F1 and F2 are. If we do this math real quick, we can actually see that this actually all adds up to 0. So we know that our horizontal geometry comes out to 0. Next for vertical components. So it's called force 1, 8 kilonewtons again, times, if we look at a triangle, we need to find using sine. Sine is opposite of hypotenuse, so it's actually going to be 3 or 8 times 3 over 5. Since this force is heading down, we're actually going to add a negative in front of it. Next we have to add our vertical component of force 2. Once again, look at this triangle, and vertical. So sine, the opposite over hypotenuse here, is also always 4 over 5. So 6 times 4 over 5. Once again, looking at our diagram, we actually see that there's no vertical components to F3 or F4, right? They're just horizontal lines going towards the left. So we stop here and check if these add up to 0.
Welcome to EDU Workspace.
So we know that both of these resultant components add up to 0, so we know our resultant force is 0.
So remember that when you have a point charge, the electric field is given by least number of voltages, K equals 9 times 10 to the 9. It's also equal to 1 over 4 pi. Epsilon is just a constant. Also remember Gauss' law. Alright, so, first region, radius less than A. Okay? We are right here in this little green dot. We have no charge there. With no charge, E is 0, so E must be 0. Okay, A less than R less than B. We're in this inner shell first, our smaller shell. This is a conductor. One of the properties is that E1 flow inside the conductor. So, 0. B less than L less than C. Now we're in this first region. Also, well, what is the total charge in that region? Q enclosed? Well, just turn it on the shell. So, now we can just imagine that it's a point charge and say, alright, so first region equals less than 1 divided by 4 pi epsilon times Q, total charge inside, so 2Q over R squared. Okay, A less than R less than B. We're in this inner shell. Alright, now we're in our outer shell. C less than R less than D. C less than R less than D. Well, do our Gaussian surface, or something right here. What is the total charge in here? Well, it must be 0. Why is that? We're inside of the conductor region. So, E equals 0. There it is. So, that. Now what happens if we are outside of everything? So now what happens if we are given the Gaussian surface outside of the system? Well, what is the total charge enclosed? Plus 2Q minus 2Q, that equals 0.
We got two equations, one, two, second one, or
we can go ahead and graph this. 0, 0, so these regions 0. B to C, right here. Get something like this, squares. And then it goes straight back to 0. Alright, now let's look at where these charges might be located. So, what is the charge on the inner surface of our smaller sphere, our smaller shell? So, if we are looking at this region right here, so now, well, the electric field must equal 0 here. There's no charge on the inside. There's nothing induced. It means to just charge. What about the outer? So right here. Well, what is our charge
700
here?
0,
0, plus 2Q. It's everything. B to C. So the electric field gives us plus 2Q charge. Plus 2Q. Alright, now let's look at what about our large shell. We go right on the tangent diameter right here. Okay, so we know that the electric field must have 0 here. That means it needs to cancel with this plus 2Q that's happening right here. That means all of the minus 2Q is going to land at the surface. Minus 2Q. Then what about this outer surface here? It's got the 0. So we have a net charge of 0 here.
130. And then I want to do the inverse.
So the outer is
so I can get there.
must equal 0. We go right on here.
68. Okay, so now I can substitute this back into this equation. Figure out what S sub B is. 700.
Welcome to EDU World Space.
Okay, so for this problem we have an inner shell and an outer shell. And the inner shell has a charge of plus 2Q, the outer shell has a charge of plus 4Q. The inner shell is bound by the radii A and B, the outer shell is bound by the radii C and D. We're looking for the electric field everywhere and see if we can find where the charges are going.
Numbers here, but we're still going
So let's go ahead and look for the electric field over there.
the magnitude and direction of the result.
So, in order to find the electric field, we're going to write down Gauss's law, which says that the clothesline integral of v dot dA equals the total charge that is enclosed in the region divided by epsilon 0. So in general, this is our Gauss's law,
The result is we're seeing x
and this is our area element. This is our total charge enclosed in the Gaussian
x
surface,
component of
epsilon 0 just
F1
and E is 1.
cosine.
So let's look for our first region, which is when we have radius less than a. So for less than a, well, we don't have any charge there, so that means that we don't have a 0. Zero, B is 0. Which says that the integral equals 0. Alright, what about if we are in between A and B, so in this shell right here? Well, if it is a conducting shell, then by definition, it must have 0 electric field. So they're the same thing. E equals 0 over Now what about this cavity between B and C? We're not for B is the answer. Systems R, C. Yep. Well, now we do have some charge. We have a total charge on this shell plus 2Q.
Looks like they did.
So, just in general, we know the formula for the electric field is zero charge. E, well, equals K, which is 1 over 4 pi epsilon, 99. K cubed, 0. Divided by our square. We can use this for our region between B and C, and we see that the electric field E now what about equals K, 1, Q, which is 2, 4, Q right here is the total charge divided by R squared. R squared is just plus. So, writing more explicitly,
but sine squared of 5 plus cosine squared of 5
K, which just comes to Q, has 1 over
square root of
okay.
2 squared.
Now what about the region C and D? So now we are in this outer ring. What is this? Well, when we are in this outer ring, remember that the electric field must equal 0 because it is a conductor. So, for the region between C to less than R plus 3D, Q right here is E equals 0.
Alright, so we're looking for some components. Question number.
Okay. And then finally, what about if we are outside of this object? So what happens is
39, we really only have 2 components. One going this way.
Well, when R is greater than D, then we have to
not, strangely enough,
just for Q, 2Q, 6Q. So we just use this formula right here.
And we have the XY direction.
Charge. And we get electric field E.
45 degrees.
1 divided by 4 pi.
Which, by the way, will make this 45 degrees also.
Times 6Q.
And then we have F2. F2 is this way. I like to draw tail to tail. 45 degrees.
Those are all of our regions. Now we're going to graph this. So if we wanted to graph it, it looks like this. We have R, and
think about what's going on here. And considering where 30 degrees is on the drawing, and that's going to be degrees.
And we are going to get
After 2, which is 150
and what about between
Makes sense. Okay, so components.
originally 0 inside of
C here.
and
F1.
between regions B and C. So because
to
1 over r squared
200
is this,
times the sine of
we see a
45
similar
meters,
function for when r
which is just the square root of 2 over 2.
This time we are going to have the vector front and
I direction. And the same thing in the j direction.
and so that's that. Now what about the charge on the inner circle?
Okay, after 2.
Inside
Well, go to the well,
okay, so
in the x direction is going to be cosine of 30. The cosine of 30 is the square root of 3 over 2 times. This is just going to be 150. What will be negative 1? Negative direction.
this time well the charge right there, there's inside
And the sine of 30 degrees is 1/2 over 8 times. This is just going to be 150 is 0. Negative Alright, so simplifying these, this one is just going to be
the outer surface right here
100
needs to contain all the charge.
100 jet. F.
And what about for our
2 is going to be negative 75 and I, comma, 75 jet.
okay. The inner. So we do a Gaussian surface right here. We know that from this having that problem 0 the only way for that to happen is also there must be an reduced negative 2 charge on the inside.
So we actually have the negative so that's the way that these forces actually to define
why is that? Because we need the next
to the horizontal
on the outer surface
300 newtons, which is told that
Gaussian surface.
the negative force
That's just the total charge. 302.
this angle right here is 10 degrees, and this angle right here is 6 degrees. So total,
And that's that.
7
Also, another thing to know about this graph is that this is, if we were to have units on this, we expect that this would be
that's just straight
taller than 6 divided by 4, 5, 2.
It's a 5, 12, 13 triangle.
Check
Yeah, for the x-axis is 13.
And that's
So
that.
we'll go ahead and sum all of our x horizontal components. F1 is 300 times cosine 5, because cosine in this case corresponds to x for horizontal. For F2
Welcome
we
to
actually don't
EDU
have
Workspace.
horizontal directly upwards.
This is
For F3 however, we'll be subtracting because this force is going in the other direction, or the opposite direction. It's just this force. And here, instead of using cosine, because we have a 5, 12, 13 triangle, we can just use 5, 12, 13 trigonometry for right triangles. So SOHCAHTOA, in this case, and cosine, adjacent over the hypotenuse, which is almost 13. So all
This force is measured by this right here will give us instead of cosine, because we have a 5 for y, for the vertical, this right here, force 1 cancel. Very similar, since I use sine. These forces go in the direction, minus this one in the opposite direction. This time we actually do include force 2. Here, 200 newtons. It's purely upwards. Finally, 180 times on sine, so opposite of our hypotenuse, is 5. This right here is this time we actually do as well. Next, we have to find the angle that forms the positive x prime axis. To do that, we use this symbol. Theta is going to equal arctan and y component over the table. So just plug in those values. Calculator was in. Divided by 1 gives us the theta value. Look at those values. 72x7.1 degrees. Remember, this angle is actually the angle between the resultant vector and the x-axis. And what we need to do is the angle between the resultant vector and the x prime axis. Remember, theta here, or sorry, the angle between the x prime axis and force 1 is 10 degrees. So if we add that to 20 degrees, then y forms a positive x-axis. Remember, this angle is actually the angle between 30 degrees vector to the x-axis, giving us a angle theta here, 42, the angle between the x and 1 degrees. And those are our final answers. Force 1 is 10 degrees. So if we add that to 20 degrees, so our result force vector, positive values, and the magnitude of 42, 71 degree angle, very positive. This angle is actually the angle between the resultant vector and the x-axis. We get theta here, 42, theta here, or sorry, the angle between the x prime axis and force 1 is 10 degrees. So if we add that to 20 degrees, this angle is actually 7 positive x-axis.
Welcome to EDU World Space.
So you can easily find them using Moss circle. To find Moss circle, we have to use between the center and the radius of the circle. The center can be found using this equation, and it is at 637.5. Zero. And the 6. And for the radius, you can find using this equation, and it is 3.
Welcome to EDU World Space.
2.51 and 6. And have to draw the circle.
Welcome to EDU World Space.
And 5 is circle. And this point will be epsilon 1, this point will be epsilon 2, this point is maximum incline shear strain.
Welcome to EDU World Space.
So for the epsilon 1 is just the average strain plus the radius, which equal to 870.
Welcome to EDU
For
World
epsilon
Space.
2 is just 405, 10.6. And the maximum incline shear strain is just 2 radius, which is 465. And now for the maximum absolute shear strain, we have to draw another circle which touch the origin and the epsilon 2, and then we draw the big circle that cover those two circles like this. And at this point, the y-axis value of this point will be the absolute maximum shear strain by 2. So it's just that absolute maximum shear strain will equal to epsilon 1, which is now for 870. And these are the origin and the epsilon 2. Then we draw the big circle that over this point.
Welcome to EDU World Space.
The absolute law is, and this problem we have to solve problem 10% using Moss circle is just to find the equivalent incline strain at the orientation of 30-degree horizontal on the original plane. So first we have to draw the Moss circles, and to draw the Moss circle we have to determine the center and the radius of the circle, which I have already done that. And then the next step is we have to determine the
Welcome to EDU World
circle,
Space.
which can be found by epsilon x and epsilon x divided by 2, which is at this point 50,
Welcome to EDU World Space.
I will call this point A, and that's our original plan. And for the new plane, which will be the 30 degrees clockwise from the original plane. In more circles, it will be 60 degrees.
Welcome to EDU World Space.
60 degree counterclockwise from the original plane, which will be at the point B. So this is the epsilon x dot and 150. This will be
Welcome to EDU World Space.
the new shear strain. And for epsilon y, it will be at this point. And for the new plane, which is epsilon y dot, 30 degrees clockwise from the original plane. So in more circles, it will be. We know that this angle is 60 degree clockwise, 85.91 degree at point B, and so that makes this angle 34.09 degree.
Welcome to EDU
So
World Space.
epsilon x is just, and for epsilon x dot is just at this point. 50.85, which is the radius, cause that angle 34.09, and plus the center is 8.54.
Welcome to homework.
But let's use equality of the power in the circuits to obtain the result. Well, the equality of power is I1 times V1 is equal to I2 times V2. Well, this is part A and right? And I1 is V1 divided by Z1 multiplied by V1. Well, the equality is equal to V2 divided by Z2 times V2, well, is the impedance. And then here Z1 divided by Z and is equal to V1 divided by V2 and 1 divided by and 1 divided by 2 all squared is equal to I2 times Z1 divided by Z2. I think further and 1 divided by 2 is equal to square root 2 divided by and 1 divided 1 divided by 2 divided by well, the solution is obtained with the given value for the impedance. So in 1 divided by 2 is equal to and 1 divided by square root of 2 is 1 divided by 8 therefore and 1 divided by 2 divided by is equal to 10 times square root of 10. The solution is obtained with
Welcome to EDU World Space.
So in this question we have been given the state of strain that we are studying, right? So in this the strain acting on the x direction is equal to 3 and everything is -5 negative 6. Acting on the y direction is equal to 550 into the raised to negative 6, right? And the shear strain is equal to negative 650 into the raised to negative 6. Right, and strain that is acting in the z direction is 0 because the s strain that is acting in the z direction, right? Now we are going to use the Mohr's circle
Welcome to EDU World Space.
right? And so in that we are going to build the circle, and for that we need the axis, and we're going to use the equation and solutions to that, right? So we have OC that is equal to the infrared value of the strain, right? So that is sum of the strings divided by 2, right, and we calculate it together is equal to 425 into 10 to the power negative 6. Right, now all we need to do is that we need to find out the radius of the circle, and we have the expression for the circle for radius as well, right? So we have under root the difference of the circle strains divided by 2 plus the shear strain divided by 2 whole square. So you have the values, you just need to plug them in, and you get that equal to 3.4, 3.8 to 1 to 1 into 10 raised to the power negative 4, right, and that is approximately equal to 348 times 2 into 10 raised to the power negative 6. Right, now what we need to do is we need to drop the circle. Right, so let's take a look at that. So now as you can see over here that this is the point A at which the rate of strain is occurring, right? So we need to measure the angle from this point, right? So now the principal strains are easy to find, right? Because we'll take the help of the circle. Now for that, principal strain is equal to 4c into 10 r, right? So you have the values, just plug them in, and you get that is equal to 7.8 circle raised to the power negative 6, right? And the other principal strain is 4c plus r, right? Again, you have the values, just plug them in, and you have your value, your answer in Newton, right? So you get 77 into 10 raised to the power negative 6. Right, now that we have this value of the principal strain, we need to find out the maximum in plane shear strain, right? That is given by this divided by 2 and it's equal to r, right? So when you shift this to over here, you can easily find out the value of the maximum in plane shear strain, right? So the other principal strain is gamma from maximum in plane, that is equal to r, and that is equal to the difference of the principal strains, right? So you have values, you just need to plug them in, and so you have your value, that is 697 to 10 raised to the power 6. Right, now since the principal strains, they have the same sign, right? They have the same sign. So same sign means that we can directly have the expression for the maximum value of the strain, a shear strain, right? That is maximum value of the principal strains is equal to 7 to 10 raised to the power negative gamma. This includes our solution. That is equal to r. That is equal to right. So you have value. Just plug them in, and we have a value that is 6. Right now, since the principal.
Welcome to EDU World Space.
So let's solve this question. So in this question we have epsilon A equals to epsilon x equals to here plus epsilon y into
So far this section seems to be exactly the same as the previous section.
gamma xy.
I don't know what is different, seriously. So, we're showing that this is 30 degrees. We're also showing that this down here is 45 degrees. But I would rather mark this as 45 degrees, and it would be 45 degrees because it all is at a right angle.
We get 2as 0
magnitude and direction.
0 6 5
Result.
now we have tau
Force result in x direction. Let's go into the 400 30 plus 800 cosine 40. Force result in the y direction is going to be
tau xy s 400 now we have tau xy gamma xy.
The resultant force is going to be the square root of x squared y squared, and the angle is going to be the inverse tangent
B comes out
y over f. The resultant force. Just put all of these into a calculator. It's important that you do the first two so that you know exactly where that figure is, whether it's downward or upward or horizontal. And so,
Welcome to EDU Workspace.
Calculator.
So in this question,
430 resultant force
right? That is 912. The tension that is divided over here is of magnitude 2 kN, right? And we are required to determine the speed along the x direction by that here, right? Now, the thing to note over here is that as is the whole load that is applied over here, right? So it means that if there is no load, so there will be no torsion present. And as there is only torsion present, it means that there would be no stresses. It means the stress in the x direction is equal to the stress in the y direction. That is in this question 0, right? And if there is no stress, so it means that there is no normal strain, right? So it means that the strain in the x direction is equal to the strain in the y direction. That is equal to 0, right? So now since this is all cleared up, let's write the strain rosette equation for 45 degrees, right? Strain rosette equation for 45 degrees.
Over the extra So we're supposed to measure clockwise so that let's check. 93,
just discuss that
21.8. Yeah, it would be positive 20.8 as measured in the clockwise direction. So we're supposed to measure
0 right clockwise system, so solve it and you can decide it.
Alright, this is really a continuation, although this is simpler than problem 63. I do have...
This is equation number 1. Now what we need to do is that we need to write the strain rosette equation for 135 degree. Now how did we get 135 degree? So 45 right, so now what we need to do is that we need to write the rosette equation for 45 degree. So we have 135 degree, so we have 135 plus cos 135 degree and sine 135 degree, right? So again these two terms would become 0 and we only left with this term, and solve it and we'll get that it is equal to negative gamma by 2, right? Let's say that this is equation number 2. Now what we need to do over here is that we are going to use the torsion formula 5.6, right, which is torsion maximum is equal